Hello there and welcome to Life Beyond Scene, where quiet curiosity settles in for the evening and even the rougher corners of science are given room to breathe. Tonight we're heading somewhere that looks harmless on a map and very often does its best to prove otherwise. We're going to the Great Lakes, those vast stretches of fresh water that many people picture as calm, cold and scenic, the sort of places where postcards are made and gulls argue over chips near the shore, which is all true. Right up until the weather turns unpleasant and the water begins behaving less like a lake and more like a sea with a bad temper. Because that is the strange thing about the Great Lakes. They sound friendly. The name itself is almost polite. Lakes. Not oceans. Not storm basins. Not giant freshwater machines that can lift and twist steel until a ship is overwhelmed. Just lakes. It is the kind of word that suggests summer cabins, damp towels, and someone insisting they are definitely going in for a swim after one more coffee. But the Great Lakes have a long record of doing something far more serious. They can build fast, hit hard, and in the worst conditions they can put enough force on a vessel to leave even experienced crews in very dangerous water. So tonight we are taking our time with a question that sounds dramatic, because it is dramatic. Why can the Great Lakes break ships in half? Not in the sense of a campfire exaggeration, and not as a line someone made up to sell a ghost story, but as a real problem tied to weather, wave shape, ship design, water loading, hidden shoals, and the very inconvenient fact that freshwater does not need to be salty to be violent. Before we get into any of that though, I would love to know where you're listening from tonight, and what the weather is doing outside your window right now. Is it windy where you are? Is it quiet? Is there rain tapping on the glass? Are you tucked under a blanket while somewhere far off, thousands of tons of water are being shoved across a lake by a gale? There is something oddly fitting about listening to a story of inland storms while the rest of the room stays still, and if this is the kind of slow, steady, deep dive you enjoy, do give the video a like and maybe subscribe as well. It helps this little corner of calm find the people who like to end the day with a strange fact, a difficult question, or a story that starts with geography and ends with the weather doing something rude to basic human confidence. Now, with that settled, let us ease into the matter properly. At first glance, the Great Lakes do not seem like the sort of place that should be able to humble ships built of steel. Many people who have never stood on their shore imagine something closer to a broad reservoir or a very oversized boating destination. In reality, these 5 lakes stretch across more than 750 miles from west to east, hold about 21% of the world's surface freshwater, and are often described by official sources as inland freshwater seas. That description is not just a nice phrase, it is a warning dressed as a geography lesson. The system is large enough, deep enough, and exposed enough to create marine conditions that deserve the same respect people normally reserve for coasts and oceans. That difference matters because ships do not care what the water is called on a map. A captain does not get extra safety simply because the label says lake instead of ocean. A hull responds to force. Cargo responds to motion. Water responds to wind. And once those three begin disagreeing with each other, labels become irrelevant very quickly. The Great Lakes can produce long fetches, rapidly building seas, violent autumn storms, and waves that arrive in a form mariners find especially nasty. Not merely high, but steep. Not simply dramatic to look at, but dangerous in the way they strike a ship, lift it unevenly, and reduce the margin for error. On some of the lakes, especially Superior, wave heights can become very large indeed, and the short-period steep waves associated with Great Lakes storms are widely recognised as a special hazard for large vessels. That last part is worth sitting with for a moment, because it gets to the centre of tonight's story. When most people imagine dangerous waves, they picture something enormous and theatrical, the kind of wall of water that announces itself from a distance as if it has hired a brass band. Great Lakes waves can be dangerous in a less courteous way. They can be close together, steep-faced, fast to build, and hard on a ship that is long, heavily loaded and already working through wind, reduced visibility and water coming over the deck. The problem is not only height, it is timing, spacing, impact, and what the vessel is being asked to do between one crest and the next. A ship that is supported unevenly can hog, sag, slam, twist, and take stresses at several points at once. That is where the phrase break in half stops sounding like folklore and starts sounding like structural engineering under punishment. The Great Lakes have supplied enough examples to keep that possibility from being dismissed. The most famous is the SS Edmund Fitzgerald, the massive ore carrier lost on Lake Superior in November 1975 with all 29 crew aboard. She was 730 feet long, loaded with taconite pellets, and when the wreck was later found, the ship was in two main pieces on the lake bed. Investigators could not fully substantiate the exact final sequence, because there were no survivors and no eyewitnesses to the sinking itself. Even so, the official investigations and later educational summaries make clear that the vessel encountered severe storm conditions, took heavy seas over the deck, and ended its voyage in a manner that permanently changed how many people think about freshwater shipping. Now, there is an important distinction to make here, especially if we're going to be careful and not wander into dramatic nonsense. Saying the Great Lakes can break ships in half does not mean every storm does this, or that vessels are snapping apart out there like dry crackers. It means the combination of wave action, cargo loading, flooding, hull stress, grounding risk, and brutal weather can create conditions in which a ship is pushed beyond what it can survive. Sometimes that failure may happen while a vessel is still on the surface. Sometimes a weakened vessel may plunge, strike bottom, and part during the sinking. In the Fitzgerald case, different explanations have been discussed over the years, and official summaries note both the uncertainty and the role of flooding, loss of buoyancy, and severe wave conditions. The point is not that there is one tidy mechanism. The point is that the lakes are fully capable of creating the sort of mechanical and environmental stress that leads to catastrophic structural failure. This is one of the reasons people who know the lakes well tend to speak about them with a tone outsiders sometimes mistake for exaggeration. It is not exaggeration, it is experience. Lake Superior alone is so large that Michigan Sea Grant notes it can sustain waves in excess of 10 meters, or about 33 feet, while also emphasizing that steep short-period waves become especially hazardous to large ships once they exceed about 5 meters, roughly 16 feet. Those are not little chop and splash conditions. Those are serious marine loads on a moving structure carrying ore, coal, stone, grain, or whatever else industry has decided would be a good idea to move before winter closes in, and autumn, of course, has a habit of showing up in this conversation. That is when the lakes and the atmosphere start having one of their regular arguments. Cold air moves over relatively warmer water. Pressure systems deepen. Winds strengthen over long stretches of open water. Forecasts begin to sound less like a pleasant update, and more like a polite suggestion to stop being heroic. Mariner's weatherlog documented, for example, that during the major November 1998 Great Lakes storm, sustained winds on Lake Superior exceeded 50 knots, with gusts over 60 knots, while recorded wave heights reached 15 feet on Superior, 20 feet on Michigan, and 20 feet on Erie, with the publication noting that higher waves likely occurred where no reporting sites were available. That same report also observed that the highest waves tend to occur at the downwind end of the lake where the fetch is greatest. In other words, the lake has room to gather itself before it hits you with what it has made. There is also something deeply misleading about freshwater in the public imagination. It sounds softer, less hostile, more manageable. No salt, no sharks, no tides worth mentioning. Surely that must count for something. It does not count for enough. Freshwater storms still build waves, wind still transfers energy, hulls still bend, water still weighs what water weighs, and when it lands on deck pounds hatch covers, forces itself through openings, or shifts the balance of a loaded vessel. It does not pause to appreciate that everyone involved would have preferred a calmer afternoon. Then there is the uncomfortable matter of closeness. Ocean swells can be enormous. but they often have a rhythm that gives a large vessel room to ride more gradually. Great Lakes waves can arrive more tightly spaced, which means a long ship may find itself supported at the bow and stern while the middle hangs, or supported amidships while the ends are less well carried. These changing support patterns matter because ships are long beams floating on a moving surface. They are not rigid bars. They flex. They are designed to flex. But like anything under repeated load, there comes a point where flexing stops being normal and starts becoming dangerous. If waves, cargo stress, flooding, or bottom contact all join the conversation at the same time, the result can become ugly very fast. Michigan Sea Grant's Fitzgerald material specifically highlights steep, short-period waves as a serious hazard for large ships, and that is one of the key reasons this topic deserves more than a dramatic title and a thumbnail with lightning in it. What makes this even more unsettling is how quickly the situation can move from uncomfortable to catastrophic. A vessel may already be taking water, already dealing with visibility problems, already compensating for wind and sea state, already operating with damage no one fully understands yet. A bad list develops. Hatches are stressed, decks are washed, radar may be compromised, a route is adjusted, another ship offers position help. Everyone involved is still working the problem because that is what professional mariners do. Then conditions worsen, the margin shrinks, and the lake stops giving second chances. In the case of the Fitzgerald, the captain reported a bad list, loss of both radars, and heavy seas over the deck shortly before the ship vanished, after which no distress call was ever received. That kind of ending is one reason the lakes have a reputation that has lasted for generations. It is also why this story is not just about shipwrecks, it is about misunderstanding scale. People underestimate the Great Lakes because they encounter them first as names learned in school, or as shorelines visited in summer, or as scenic drives with ice cream available nearby. They do not meet them first in November, through spray and darkness, while the wind is trying to rearrange the water into something steep, hard and fast enough to hit steel like a repeated hammer blow. The lakes are not pretending to be oceans. They do not need to. They are large enough to be dangerous on their own terms, and mariners who have spent enough time on them understand that the term inland sea is not a metaphor designed by tourism boards. It is practical language for practical risk. So when we ask why the Great Lakes can break ships in half, we are really asking several smaller questions that pile up into one very serious answer. We are asking how wind builds waves over fetch. We are asking why wave spacing matters as much as wave height. We are asking what happens to a loaded hull when it is lifted unevenly. We are asking how water on deck becomes weight, then leverage, then structural trouble. We are asking what hidden shoals and low water can do when navigation is already difficult. We are asking why a place that looks so ordinary on a clean blue map can behave with such force once the weather begins pressing on it. Those are the pieces we need. Not one grand mystery, not one spooky sentence. Several real factors, each bad enough on its own and much worse when combined. And since the best way to understand a dangerous machine is to see how all its parts work together, the next thing to do is start with the lakes themselves. Because before a ship bends, before a deck is swept, before a storm earns a name in memory, there is a simpler fact waiting underneath it all. These are not merely lakes in the casual sense people use that word, and the sooner we treat them as inland seas with their own rules, the sooner the rest of the story starts to make hard, uncomfortable sense. The first thing to get straight is that the Great Lakes are badly named for anyone who has never seen them in weather. The word lake sounds contained, it sounds manageable, it suggests a shoreline that is never very far away, and water that behaves itself once the summer boats have gone home. The Great Lakes are not like that. The US Environmental Protection Agency describes them as vast inland freshwater seas, stretching more than 750 miles from west to east, and holding about 21% of the world's surface fresh water. That is not casual language. It is a more accurate way of describing what these waters actually are when wind, distance and weather begin working together. That scale changes everything. A small lake can be troublesome, certainly, but it does not usually develop the sort of marine identity that requires a deep water navigation system running from Duluth, Minnesota to Ogdensburg, New York. The US Army Corps of Engineers says the Great Lakes navigation system spans 1,600 miles and includes dozens of commercial harbours, miles of breakwaters and jetties, and more than 600 miles of maintained navigation channels. Those are not the features of a place people cross on a whim because the afternoon looks pleasant. They are the features of a working marine network, one that supports large commercial traffic across open water, where weather and wave conditions matter in the same hard, practical way they matter at sea. From the deck of a ship, this becomes obvious very quickly. The horizon is wide, the water is open, and on some routes there is no sense of hugging a friendly shore every few minutes. You're in transit for real, with distance behind you and distance ahead of you. That is one reason the National Weather Service handles Great Lakes forecast within its marine forecast system. On its marine services pages, Great Lakes forecasts are grouped with coastal and marine forecast zones, produced by forecast offices with marine responsibility. The government does not build that sort of forecast structure for oversized ponds. It does it for waters where vessels, crews and shore communities need to know what the wind, waves, visibility and warnings are doing, because the consequences are maritime, not decorative. Another sea-like trait is the way these lakes influence the atmosphere above and around them. Large water bodies store and release heat differently than the land beside them, and the Great Lakes are large enough to shape regional weather in a serious way. The National Weather Service explains lake effect snow as a process in which cold air moves over the relatively warm open waters of the Great Lakes, takes up heat and moisture, rises, and forms narrow bands that can drop 2 to 3 inches of snow per hour or more. A body of water has to be substantial before it begins modifying the lower atmosphere that way. When a lake can help make its own weather, and do it across multiple states and provinces, you're no longer talking about something that merely sits in the landscape. You're talking about a freshwater basin that behaves with some of the same large-scale energy exchange people associate with coastal environments. It gets even more sea-like when you stop looking only at the surface and start paying attention to how the water moves as a basin. The Great Lakes are considered non-tidal in the ordinary sense because their true astronomical tides are very small, less than 5 centimetres in spring tide conditions according to NOAA. Yet NOAA also notes that wind and barometric pressure can produce seechies, oscillating waves that can be several feet high, with high and low periods often arriving 4 to 7 hours apart. That means the lakes can slosh from one end of a basin to the other, strongly enough that people sometimes mistake the effect for a tide. So even where they differ from the ocean, they do so by producing their own version of large water movement, one driven mostly by weather rather than lunar pull. That is not a technical footnote. It is one more reason these lakes demand marine thinking. The shoreline tells the same story. The National Weather Service warns that dangerous currents and breaking waves are common in the Great Lakes region. It specifically notes that even small waves can hit with the force of a car, and that waves over about 3 feet are often associated with dangerous currents. On the safety side, that guidance is aimed at swimmers, not freighters, but the principle matters because it shows how much energy these waters can carry close to shore, even outside the kind of storm conditions most people imagine when they hear the word dangerous. The same NWS page explains that Great Lakes waves often come in rapid succession, around every 3 to 4 seconds on average in summer, and that waves reflecting from piers can combine with incoming waves to become steeper and larger. In other words, even at the beach, these lakes are already doing the sort of short-period, forceful wave work that makes mariners pay attention. This is where the inland sea idea becomes more than a scenic description. It becomes a mechanical one. Wind has room to build across these long stretches of open water, and that open water distance, or fetch, matters a great deal. Michigan Sea Grant's teaching material on the Edmund Fitzgerald states plainly that wave height on the lakes is primarily a function of wind speed and fetch. and that steep, short-period waves can be particularly hazardous to large ships, especially once they exceed about 5 meters or 16 feet. The same source notes that Lake Superior, because of its size, is capable of sustaining waves in excess of 10 meters, about 33 feet. A place that can generate 33-foot freshwater waves and deliver them in a steep pattern that is especially hard on big ships is not behaving like a casual recreational lake. It is behaving like a serious marine basin with its own rules, and it does not much care whether the people reading the chart are charmed by the word freshwater. There is also the matter of how quickly conditions can become operational, rather than scenic. The Great Lakes navigation system exists because commercial movement here is constant and important enough to require dredging, channel maintenance, coastal structures, hydrographic surveys, navigation notices, and updated project information. The Army Corps even notes that channel conditions can change rapidly, which is not the sort of sentence anyone writes about water they consider simple. Add in the marine forecast framework from the National Weather Service, the buoy and observation systems used to monitor conditions, and the long history of commercial shipping across these basins, and the identity of the lakes comes into focus. They are inland in geography, certainly, but in the daily life of navigation they function as a marine environment, with all the planning, caution and infrastructure that implies. The weather reinforces that identity in every season. During colder months, the open water helps generate lake-effect snow. During storms, wind and pressure can push the lakes into seeches and water level swings. Along shore, breaking waves and currents create conditions that are dangerous even for people who never leave sight of land. Offshore, the same scale and energy matter to vessels, measured not in feet of shoreline stroll, but in hundreds of feet of steel, cargo and draft. That is why the phrase inland sea is useful. It tells you in a few words that these waters have marine reach, marine weather influence, marine hazards, and marine consequences, even though they are fresh and enclosed by land. There is a psychological trap in all this, and it is a simple one. People hear ocean and prepare themselves to be humbled. They hear lake and assume there is a limit to how unpleasant things can get. The Great Lakes punish that assumption. Their scale gives windroom to organise itself. Their basins let water move in ways that surprise people who think only in terms of tides or static shorelines. Their weather influence is strong enough to build intense snow bands. Their waves can be close together, steep and relentless. Their currents can be dangerous even at the beach. Their shipping lanes are large enough and busy enough to need the same sort of warning and forecast culture that belongs to marine operations. By the time you add all of that together, the phrase inland sea no longer sounds dramatic. It sounds restrained. And once that scale is fixed in the mind, the next piece becomes easier to understand. A body of water this large does not need an ocean tide or a hurricane name to become dangerous. It only needs wind, distance, and enough open surface for the water to stop looking calm and start building itself into something a ship has to survive. What makes the Great Lakes dangerous is not only how bad they can get, but how ordinary they can look shortly before they get there. That is the part people underestimate. Calm water suggests safety because the human brain likes stable surfaces. If the horizon is level, and the shoreline looks patient and the wind is not yet doing anything theatrical, most of us assume we have time. On the Great Lakes, that assumption can expire quickly. NOAA researchers note that while people often think of Great Lakes wave conditions as generally mild, intense storms and rapidly changing weather patterns can generate severe sea states that become serious hazards to mariners. The National Weather Service treats that volatility seriously enough that marine weather statements are specifically used to alert people on the water to rapidly changing conditions, including increasing winds, thunderstorms, dense fog, snow squalls, and strong rain showers. The important point is not simply that bad weather exists. It is that the lakes can move from manageable to threatening on a timescale that punishes hesitation. That is one reason calm water can be misleading, even before the first large wave arrives. A lake does not need to look dramatic at noon to become dangerous by late afternoon. Wind begins transferring energy to the surface long before the full result is visible to someone who's only glancing out from shore or judging conditions by instinct. The Great Lakes are large enough that once a sustained wind has room to work across open water, the surface can organize into a sea state with real force behind it. Michigan C. Grant explains that wave height on the Great Lakes depends mainly on wind speed and fetch, the distance over which the wind blows across the water. That sounds simple, but it has serious consequences. A vessel may begin its passage in tolerable conditions and then find itself in water that has had hours to build. By the time the waves look dangerous, the underlying energy has already been gathering. It is a bit like realizing too late that the argument started long before anyone raised their voice. The next trap is that Great Lakes waves are not only about size, they are also about shape and spacing. Many people imagine danger in terms of height alone, which is understandable because height is what photographs well. Mariners know better. The National Weather Service has found that wave periods during current-related incidents on the Great Lakes typically fall between 4 and 5 seconds, which is considered short-period wave action. By contrast, ocean incidents are more often associated with longer wave periods, generally above 9 seconds. Michigan C. Grant adds that steep, short-period waves are particularly hazardous to large ships, especially when they exceed about 5 meters or 16 feet, and that Lake Superior can sustain waves over 10 meters, roughly 33 feet. What this means in plain language is that the water does not simply rise and fall under a ship in a gentle, roomy pattern. It can hit in quick succession, forcing a long vessel to respond again and again before it has properly recovered from the last motion. A wave does not need to be cinematic to be dangerous. It only needs to arrive at the wrong angle, with the wrong spacing for long enough. That short spacing matters because ships are not magic. They are floating structures under load. They flex, and they are designed to flex, but only within limits. A long ship in closely spaced steep seas can be lifted unevenly, with one part of the hull strongly supported while another is not. If enough of that loading repeats, and if other problems begin to stack on top of it, the lake stops being a weather problem and becomes a structural problem. This is one of the reasons the phrase, "the Great Lakes can break ships in half," is not just an eerie line people repeat around November. Severe sea states on these lakes can punish a hull through repeated slamming, bending, twisting, deck loading, and the sheer fatigue of being forced to answer one sharp wave after another. Michigan C. Grant's Fitzgerald material is careful about exact causes in that famous sinking, but it is equally clear that Great Lakes conditions can be extremely treacherous, and that steep, short-period waves are especially hazardous to large ships. Once you understand that, the water stops looking merely rough and starts looking mechanical. There is also the matter of how danger can persist even when the lake appears to have settled down. NOAA's work on meteor tsunamis notes that several notable Great Lakes events involving injuries or fatalities occurred when the waves arrived at shore, hours after the storm that generated them had already passed, under relatively quiet atmospheric conditions. That is a deeply inconvenient feature of large water systems. The hazard and the visible weather do not always remain politely attached to each other. A person can look out, see calmer skies, and assume the lake has stopped misbehaving, only to meet a surge or oscillation with far more energy than the scene appears to deserve. NOAA's tide and current information for the Great Lakes also explains wind setup and seachers. When strong winds push water toward one end of a lake, levels can rise there and fall elsewhere, and when the winds shift or stop, the basin can continue oscillating like water in a bathtub. So the calm that follows a storm is not always true calm. Sometimes it is only the visual part of the storm leaving before the water has finished the discussion. That helps explain why the lakes can feel unfair. People like hazards that announce themselves clearly. We are much happier with danger when it wears a large, obvious hat. The Great Lakes do not always bother. The National Weather Service warns that even small waves on the Great Lakes can hit with the force of a car. It also reports that 85% of current-related incidents occur when waves are 3 feet or greater. 3 feet is not the sort of number that impresses someone who has seen dramatic surf footage online. It sounds almost modest. Yet on these lakes, short-period waves at that size are enough to create conditions linked with dangerous currents, knock people off balance, and turn shorelines, piers and breakwalls into places where one bad step can become a rescue call. If water can do that to a swimmer or walker in what many would call not even that rough, it should not surprise us that larger, more exposed operations can go from routine to serious trouble with alarming speed. And then there is cold water, which is one of the great cheats in this entire story. Cold water allows the lakes to be dangerous even when the air is pleasant enough to talk someone into making a foolish decision. The National Weather Service warns that cold water shock and hypothermia are real threats on the Great Lakes, especially early in the season, and says plainly that cold water is a huge hazard that can kill. The Coast Guard's cold water survival guidance breaks immersion into 4 stages and notes that an initial cold shock response can occur in water below 77 degrees Fahrenheit, with the most severe shock occurring in the 50 to 59 degree range. That means a person does not need to wait for true winter to be in grave danger. Sudden immersion can produce involuntary gasping and rapid breathing long before classical hypothermia becomes the headline problem. So a lake that looked calm enough for a small craft outing or a deck crossing can become catastrophic, not only because the weather worsens, but because any mistake that puts someone in the water has a much shorter survival window than intuition suggests. Freshwater may look gentler than the sea, but the body does not care what word was used on the map. For larger vessels, cold water changes the meaning of every other failure. A disabled engine is more serious. Flooding is more serious. A man overboard event is more serious. The lake is not merely trying to drown you in the broad dramatic sense. It is reducing your time to think, to work, to fix, to retrieve, to survive. Once cold shock enters the picture, even strong swimmers are operating on borrowed competence. The Coast Guard notes that cold water immersion can trigger involuntary gasping and rapid breathing, which can quickly create a drowning hazard. That matters because people often imagine ship losses as long sagas in which everyone has time to make calm decisions while alarms ring in the background. Sometimes there is time, sometimes there is not. If weather, darkness, icing spray, cargo stress and flooding are already complicating the situation, the cold water below removes a great deal of the mercy people assume is available once the vessel itself is lost. A calm-looking lake with cold water is, in its own way, already primed for catastrophe before the wind even sharpens. Another reason these waters turn from ordinary to dangerous so quickly is that the Great Lakes are not passive scenery. They are active systems that can modify local conditions and create their own operational complications. The same large water properties that help produce lake effect weather also help generate visibility and navigation problems that layer onto the wave problem. The National Weather Service notes that marine weather statements can cover dense fog and snow squalls, along with rising winds and thunderstorms. In practical terms, that means a vessel or small craft can face worsening seas at the same time that its situational awareness is degrading. You're not just dealing with more force on the water, you may also be dealing with less information, less visual reference, and less confidence in what is developing nearby. That combination is what turns an inconvenience into a cascade. A crew that can manage waves in clear conditions may struggle far more once visibility drops, and every correction has to be made with poorer information. The lake becomes catastrophic, not because one thing goes wrong, but because several things begin going wrong in company, and each one makes the others harder to handle. There is a basin-wide version of that same problem as well. Wind setup and seeches mean the lake can reorganize its own water levels over hours, altering what shore, harbour and basin conditions feel like from one time block to the next. NOAA explains that strong winds can pile water up at one end of a lake, and then, once those winds shift or weaken, the water can oscillate back and forth. NOAA also notes that seeches are a coastal flooding phenomenon, on large lakes such as the Great Lakes, producing abnormally high and low water levels on opposite sides of the basin in a short period of time. On paper, this sounds like a clean little hydrology lesson. In reality, it means docks, marinas, harbour mouths, shoreline infrastructure, and nearshore operations can all experience abrupt, weather-driven water level behaviour that feels deeply unreasonable if you expected the lake to remain still once the wind backed off. Calm on the surface is not always stability underneath. Sometimes it is only the point in the cycle where the trouble is changing shape. People on shore receive a milder version of this lesson every year. The National Weather Service's Great Lakes current incident data shows an average of 12 fatalities and 23 rescues each summer due to dangerous currents. That is not the profile of a harmless recreational backdrop. It is a reminder that the lakes often become lethal in conditions people fail to classify correctly. Not every fatal day looks like a storm day. Not every dangerous shoreline looks frightening in a photograph. Sometimes the water only looks busy. Sometimes it looks inviting in all the wrong ways. That is why the phrase "know before you go" appears so often in Great Lakes safety messaging. It is less a slogan than a confession that what the lake looks like from a parking lot is often not enough information to protect you. The leap from calm-looking to catastrophic is smaller than people think, and it is often hidden inside wave period, current formation, temperature, and changing local weather rather than in some grand obvious visual cue. For ships, the same principle holds at a larger and more unforgiving scale. A voyage rarely becomes catastrophic because someone looked out the window and saw immediate disaster in plain sight. Trouble usually builds in layers. The forecast worsens, the sea state gets steeper, water starts coming aboard, speed and heading decisions become more consequential, visibility reduces, equipment problems become harder to isolate because the environment itself is now attacking the ship from several directions. The Great Lakes are especially good at creating these stacked conditions because their weather can change quickly, their waves can be steep and close together, and the water underneath any failed response is cold enough to make recovery harder and more urgent. Calm water can become catastrophic because catastrophe here is cumulative. It is not always one towering moment. Sometimes it is 5 or 6 reasonable concerns arriving fast enough to become one unreasonable situation. That, in the end, is why the lakes are so often misunderstood. They do not need to look dramatic for danger to be real. They only need room for the wind to build, enough open water for waves to organise into steep short periods, a temperature that punishes immersion, and a weather pattern willing to change faster than human confidence. Once those ingredients are present, the shift from ordinary to catastrophic is not mysterious at all. It is physical, measurable, and repeatedly documented. The water may start the day looking flat enough to reassure people into poor decisions, but the lakes do not owe anyone a long warning. They are large enough to act like seas, restless enough to rearrange their own surface and shorelines, and cold enough to turn small errors into terminal ones. And once you see that, the next question is not why they become dangerous, but exactly how the wind uses all that open distance to build the kind of waves that can begin bending steel. One of the reasons people misread the Great Lakes is that wind looks so ordinary. It is invisible, common, and easy to underestimate until it starts turning a flat surface into a mechanical problem. But giant waves do not appear out of nowhere. They are built step by step by a very specific set of conditions. National Weather Service marine training materials reduce that process to the essentials: wind speed, fetch, and wind duration. Wind speed is how hard the atmosphere is pushing. Fetch is the distance over open water across which that push can keep working. Duration is how long the push continues. When those three line up well enough, wave growth accelerates. If they persist long enough, the water can reach what forecasters call a fully developed sea, meaning the waves have grown as much as the existing wind and available distance really allow. That sounds tidy on paper, but on the Great Lakes it translates into something much less comfortable. A large body of fresh water turning wind into repeated impacts against hulls, decks, break walls, and shorelines. Fetch is the part many people never think about, even though it is one of the main reasons the Great Lakes can become brutal so quickly. A gust over a small pond can wrinkle the surface. The same gust sustained over a broad stretch of open water has room to work. It does not merely ruffle the top. It transfers energy continuously, allowing small ripples to become organised waves, then larger waves, then a whole field of moving water with enough momentum to damage structures and exhaust crews. Michigan Sea Grant states this plainly in its material on the Edmund Fitzgerald. The height of waves generated on the lakes is primarily a function of wind speed and fetch. That one sentence explains a great deal of Great Lakes danger. It tells you that once the wind finds a long enough path across open water, the lake stops behaving like a pleasant geographical feature and starts behaving like a machine with a lot of leverage. The size of the basins gives that leverage room to become serious. Lake Superior alone is about 350 miles long and 160 miles wide, with a water surface area of roughly 31,700 square miles, according to Michigan Sea Grant's Lake Facts. That scale matters because giant waves are not made by wind alone. They are made by wind having enough uninterrupted room to keep pressing on the surface. Lake Michigan studies cited in NOAA's library show that strong winds with long fetch distances of roughly 400 to 500 kilometers along the lake's longitudinal axis are associated with fully developed extreme wave conditions. Put more simply, when the wind runs with the shape of the lake instead of across a short section of it, it gets far more time and distance to build something ugly. A narrow burst of roughness can become a long corridor of force. This is why the orientation of a lake matters almost as much as the wind itself. If the atmosphere happens to push along the long axis of the basin, the fetch grows and the wave field has room to organise into something larger and more dangerous. National Weather Service material on past Great Lakes storms notes that strong southwest winds running up the long axis of Lake Michigan built high waves that struck ships on the northern and eastern sides of the lake. That is a very practical reminder that geography and weather collaborate. The shape of the lake decides how much room the wind gets, and the wind decides what to do with it. A storm tracking in one direction may produce unpleasant but manageable conditions, while a storm aligned with the long reach of the basin can turn the same water into a battering surface with very little mercy in it. Wind duration is the next part of the process, and it is easy to overlook because people tend to focus on peak gusts rather than persistence. One dramatic gust can make the water look aggressive, but sustained wind is what really grows a wave field. The National Weather Service's marine training material treats wind duration as one of the fundamental controls on wave growth, because the water needs time to respond. Energy is not dumped all at once, it accumulates. That is one reason a lake can look merely restless at first, and then much worse a few hours later, even if the general weather pattern has not changed much to the casual observer. The air has simply kept pushing long enough for the waves to mature. By the time a vessel meets those larger waves, the problem has been developing for hours out across open water, where no one on shore was necessarily paying attention. The Great Lakes add one more complication that makes wave growth especially unpleasant. The atmosphere over them is often unstable during the fall and early winter. The National Weather Service's Fitzgerald Science page notes that research showed the wind speeds and fetch distance needed to generate the same wave heights are lower in an unstable atmosphere than in a stable one, and it adds that the atmosphere over the Great Lakes is frequently unstable during fall and early winter. That means the lakes do not always require the neat textbook version of extreme wind plus enormous distance to build severe waves. Cold air moving over relatively warmer water can make the boundary layer more efficient at transferring momentum, so the atmosphere gets more effective at roughening and growing the surface. This is one reason autumn Great Lakes storms have such an ugly reputation. The season itself makes the wind better at its job. Once those ingredients line up, the lakes can produce wave heights that stop sounding inland very quickly. Michigan Sea Grant notes that Lake Superior can sustain waves in excess of 10 meters, or about 33 feet, and emphasizes that steep, short-period waves are particularly hazardous to large ships once they exceed about 5 meters, around 16 feet. NOAA's discussion of the Great Lakes Wave Prediction System also highlights the need for accurate severe sea state forecasts, because hazardous wave conditions on the lakes affect vessels, coastal communities, and public safety. A freshwater wave does not need salt in it to hit hard. 33 feet of fresh water is still 33 feet of moving mass, and the ship receiving it is not reassured by the chemistry. The lake has taken wind, fetch, season, and duration, and converted them into repeated force. It helps to remember that forecast wave heights do not even describe the very biggest waves a ship may meet. NOAA defines significant wave height as the average height of the highest one-third of the waves, and notes that individual waves may be more than twice that value. That means a forecast or report of, say, 17-foot significant wave height is not describing a uniform parade of identical 17-foot waves marching past in good order. It is describing a sea state in which some waves are smaller, some are larger, and a few can be substantially larger than the reported number. In bad conditions, the lake is not delivering a tidy, predictable set of equal impacts. It is delivering a spectrum, which is exactly the sort of thing that makes structural stress, deck loading, and timing decisions harder. The average already looks bad, and the worst moments are worse than the average. There is another Great Lakes feature that makes these storms especially punishing. The waves are fetch limited, which means they often have shorter periods than ocean swells. National Weather Service. Great Lakes Safety Guidance says waves on the lakes come in rapid succession, every 3 to 4 seconds on average in the summer. Current incident summaries from the NWS also say Great Lakes wave periods are typically 4 to 5 seconds, and often less than 7 seconds because of fetch limitation. That gives the water a more relentless character. There is less room between impacts, less time for recovery, and more repeated loading in a shorter span. For swimmers, that means exhaustion. For vessels, it means the hull keeps answering one force after another with very little rest in between. Giant waves do not only become dangerous because they are tall, they become dangerous because they are frequent, steep, and insistent. Historical storms show what this looks like when the ingredients line up properly. The National Weather Service's White Hurricane page says, the November 1913 storm brought hurricane-force winds to the Great Lakes and remains the largest inland maritime disaster in US history by number of ships lost, with an estimated 250 lives lost. For a more instrumented example, the NWS summary of the October 26 to 27th, 2010 extratropical cyclone notes that Rock of Ages on Lake Superior recorded a sustained wind of 68 miles per hour with gusts to 78, while a western mid-lake buoy reported significant wave heights up to 18.7 feet, and a Canadian buoy farther north reached 26.6 feet. Those are not sentimental stories from an old dockside bar. They are records of what happens when a lake that is large enough, long enough, and exposed enough is driven hard by a major system. The making of giant waves is also not uniform across the lake. Mid-lake conditions can differ sharply from nearshore conditions because the open basin gives the wind more effective fetch and fewer interruptions. NOAA library material on Lake Michigan wave modelling points out that the spacious mid-lake region can generate fully developed deepwater waves, while coastal winds are more impeded by irregular shorelines, and nearshore waves are altered by shallow water processes such as depth-induced breaking. That distinction matters to mariners because a shoreline observer can badly underestimate what is happening farther out. The coast may show rough water and whitecaps, but the mid-lake may be running a much more mature and dangerous wave field. In other words, the giant waves are often built offshore where the lake has room to work, and they do not need the beachgoer's approval before becoming a serious navigation problem. The shore, however, eventually gets involved, because waves do not remain abstract once they start moving landward. NOAA's coastal education material explains that As wind-driven waves approach shore, friction with the bottom causes them to steepen, and once they become too steep and unstable, they break. On the Great Lakes, that nearshore steepening adds another layer of trouble. Large storm waves already generated over open water can become more chaotic and forceful, near harbour mouths, shoals, breakwalls, and piers. For a ship seeking refuge, that means the hardest part may not always be out in the deepest water. It may be during approach, when the basin's built-up energy starts interacting with bottom shape and coastal structures in ways that sharpen and focus it. The lake is not finished once it has made the wave. It keeps modifying the wave all the way in. So when people say the wind made the waves, that is true, but it is not complete. The wind began the work, the fetch gave it room, the duration gave it time, the season, especially in unstable autumn conditions, made the transfer more efficient. The long axis of a lake sometimes handed the storm a perfect runway. The open mid-lake allowed the wave field to mature. The shorter periods made the result more relentless. Then the shoreline and the bottom started changing the waves again as they moved toward ports, shoals and structure. By the time a captain faces that finished product, the lake has spent hours assembling it. And once it arrives, the next problem is not only how high those waves are, but how little breathing room they leave between one blow and the next. One of the most deceptive things about Great Lakes storms is that people tend to focus on how high the waves are and overlook how often they arrive. Height is easy to picture. A 20-foot wave sounds dangerous because it is dangerous, but spacing matters just as much, and sometimes more. The National Weather Service defines wave period as the time between one wave crest and the next. On the Great Lakes, those periods are often short because the waves are fetch limited, meaning the wind has a finite stretch of water to work across rather than an ocean-sized runway. Great Lakes current incident summaries from the NWS say, wave periods are typically about 4 to 5 seconds and often less than 7 seconds. In other words, the water does not give much breathing room. One crest hits, the ship reacts, and before that reaction has fully settled, another crest is already arriving. That quick timing is part of what makes Great Lakes water feel different from the image many people carry in their heads when they think about big waves. Ocean swell can be very large, but it often has longer periods, which means more distance and time between crests. The Great Lakes often produce a choppier, steeper pattern. The National Weather Service's Great Lakes Safety Material says waves on the lakes come in rapid succession, around every 3 to 4 seconds on average in summer, and local NWS beach hazard guidance warns that these waves can come in fast and close together, leaving much less time to recover between hits. That guidance is often written with swimmers in mind, but the underlying physics does not stop mattering when the target is a ship instead of a person. Less time between crests means less recovery time for everything in the water. That is where wave period turns into structural trouble. NOAA's Marine Forecast, FAQ, states plainly that the danger presented to a vessel is a function of wave steepness, as well as wave height, and that at a given wave height the danger increases as wave period decreases. That is a compact way of saying something important. If two waves are the same height, the one with the shorter period is generally steeper and more abrupt. It rises faster, drops faster, and pushes a hull harder in a shorter amount of time. NOAA's marine navigation pages add that steeper waves present a higher risk for capsizing vessels or damaging marine structures. So the Great Lakes do not need to outdo the ocean in pure height every day to become very unpleasant. They only need to build waves that are close together enough to be steep, jolting, and relentless. That steepness is one of the reasons Great Lakes waves have such a rough reputation among mariners. Michigan Sea Grant states that steep short-period waves can be particularly hazardous to large ships such as the Edmund Fitzgerald, especially when they exceed about 5 meters or 16 feet, and it notes that Lake Superior can sustain waves over 10 meters, about 33 feet. That sentence matters because it cuts through a common misunderstanding. The problem is not simply that the lakes can produce high waves. The problem is that they can produce high waves in a form that is especially hard on large vessels. A long ship does not just go up and down, it pitches, rolls, bends, twists, pounds and sheds spray, all while trying to keep cargo, heading and structural loads within something resembling reason. When the waves come too close together, the ship spends less time riding them and more time being worked by them. It helps to think of a ship not as a solid bar, but as a very long floating beam. Classification societies and naval engineers treat it that way, because the hull is constantly subject to bending moments from the changing distribution of weight and buoyancy. Lloyd's Register explains that when a ship rides a wave crest amidships, the hull is in a hogging condition, arching upward in the middle, while when the ship is supported by crests near the ends with less support in the middle, it is in sagging. The US Navy's salvage manual uses the same terms and notes that heavy seas can cause both conditions. That means every time a long vessel meets a pattern of closely spaced waves, the support under the hull keeps changing. The sea is effectively moving the ship's support points around underneath it, over and over again. If the wave pattern is steep, short and persistent, those bending loads repeat with very little rest between them. That repetition is what makes short-period water so exhausting for both ship and crew. One large wave by itself is a problem. A long sequence of steep waves arriving every few seconds is a process. The ship is being forced into constant response. The bow rises and falls sharply. The stern lifts and drops. The middle section alternately takes more and less support. The deck gets swept. Water tries to move where no one wants it. Equipment, fittings, hatch covers, lashings, and people are all being asked to endure repeated shock loading. Great Lakes beach hazard material from the National Weather Service says short-period waves repeatedly hit and wear down swimmers through fatigue. That is obviously about people in surf, not steel hulls in open water, but the idea carries over cleanly. Repeated impacts are dangerous because they reduce the ability to recover. Fatigue is not only a human problem, it is also what repeated stress does to hardware, seams, fittings, and judgment. There is another practical problem with closely spaced waves. They interfere with timing. Mariners do not only need a ship that is strong enough, they need one that can be handled well in the water it is in. A vessel meeting head seas, quartering seas, or following seas has to manage speed and heading carefully. With longer wave intervals, there is at least a little more time to read the motion and respond. With shorter intervals, the whole pattern becomes more abrupt. Corrections have to be made faster. Motions stack on each other. Green water comes aboard more readily. If the ship is already taking spray, icing or water over the deck, the crew gets less time to assess each hit before the next one lands. NOAA's marine warning and forecast systems exist in part because hazardous wind and sea conditions for mariners are not only about spectacle. They're about operations becoming steadily harder to manage as sea states sharpen. Then there is the unpleasant fact that reported or forecast wave height is not a promise that every wave will be that size and no more. NOAA explains that significant wave height is an average of the highest third of the waves, not the single largest wave in the sequence, and notes that a wave much larger than the current wave sequence can occur. The NWS forecast parameter guidance likewise notes that in a forecast sea state some individual waves will be notably higher than the significant wave height. That matters because a short period sea does not deliver one identical punch over and over. It delivers a range of impacts, some moderate, some severe, and a few worse than the number everyone was staring at in the briefing. If the vessel is already being worked hard by a steep, closely spaced pattern, an unusually large individual wave can arrive at exactly the wrong moment, increasing deck loading, flooding risk, or structural stress. On the Great Lakes, this pattern is especially uncomfortable because fetch-limited waves tend to be short enough in period to keep the whole sea state busy. The NWS swim season summaries say Great Lakes wave periods are often less than 7 seconds because of fetch limitation. That is a useful reminder that wave fields on the lakes are not miniature oceans. They are their own category of problem. The water has had enough room to build dangerous height, but not enough room to stretch into the longer, more spacious swells people often associate with the open sea. So the result is not just big. It is compact, energetic, and repetitive. It is a crowded pattern of motion, which is exactly the sort of thing that can make a ship work harder than an outsider expects from an inland body of water. This is also why the lakes can be nasty even before the wave height reaches the sort of number that makes headlines. The National Weather Service says dangerous currents on the Great Lakes become more likely once waves exceed about 3 feet, and beach hazard guidance warns that high waves that come in fast and close together can quickly wear people out and wash them from piers and break walls. Again, that guidance is written for shore safety, but it exposes an important truth. Closely spaced wave energy becomes hazardous at relatively modest heights because the cadence itself is punishing. A ship does not wait for a monster wall of water before it begins taking punishment. Repeated 8-foot or 10-foot steep waves every few seconds can already produce a miserable operating environment, especially if wind, spray, darkness, freezing conditions or shallow water effects are adding their own complications. For a long commercial vessel, the relationship between wave spacing and hull length becomes especially important. Lloyd's Register explains that the largest bending moments occur in conditions such as sagging, when the ship's ends are supported by wave crests, and hogging, when the crest is near midships. If the wave train is arranged so that these support patterns keep changing rapidly, the hull girder is continually cycled through different stress states. On a heavily loaded ship, that matters a great deal because the hull is not only carrying itself, it is carrying cargo, fuel, machinery, and the accumulated effects of prior service. The sea is not attacking an empty beam in a clean laboratory. It is attacking a working vessel already under significant load, and it is doing so in a rhythm that may be too fast to feel merciful. The uncomfortable part is that the most dangerous result may not come from one dramatic motion everybody notices. It may come from repetition. The hull works, the deck works, the fittings work, the hatches work, and the cargo works. Then water starts coming aboard and adding weight when no one wanted weight. Then the bow slams a little harder. Then the vessel buries itself slightly deeper into one trough. Then another steep crest lands before the ship has fully recovered from the last impact. Great Lakes Wave Model research at NOAA notes that intense storms and rapidly changing weather patterns can generate severe sea states on the lakes. Put into plain language, that means the water can build and stay ugly long enough that a ship is not merely surprised by it, but continuously worked by it. In closely spaced waves, the danger is cumulative. This cumulative effect is one reason the Edmund Fitzgerald still matters in conversations like this. Michigan Sea Grant's material on the storm that sank her stresses that steep, short-period waves are particularly hazardous to large ships. Investigators never fully settled every detail of the final loss, but the broader lesson remains sound. Large Great Lakes freighters are not immune to short-period seas simply because they are large. In some ways, their length makes the loading problem more interesting and more dangerous, because the farther apart the bow, midships and stern are in relation to the wave pattern underneath them, the more scope there is for uneven support and repeated bending. A vessel that looks immensely strong in calm water is still at the mercy of how the lake chooses to hold it up from one moment to the next. There is also a human side to short spacing that deserves more respect than it usually gets. Closely spaced waves are tiring to watch, tiring to stand in, tiring to work in, and tiring to think in. Every movement on board becomes less efficient. Every inspection is more awkward. Every judgment is made in a more physically demanding environment. On smaller boats, that can become a capsize or man overboard problem. On larger ships, it becomes a systems management problem. Crews are trying to interpret weather, watch for flooding, assess equipment strain, maintain course, and preserve the vessel while the lake keeps striking from below and from the side, with very little pause. The shorter the period, the more this becomes a contest of endurance. a sea that never quite lets the ship settle, is often more dangerous than a sea that is merely tall. And the closer those waves come together, the less forgiving the next stage becomes when the ship approaches land, shoals, harbour entrances or underwater features. A steep wave field in deep water is already bad enough. A steep wave field moving over shallower areas, interacting with bottom shape and starting to change form as it nears reefs, bars and rock is where the lake begins adding hidden teeth to the visible blows. What makes the Great Lakes especially unpleasant is that the danger is not only above the water, it is also below it. Wind and waves get the headlines because they are the dramatic part. You can hear them, you can see them. They throw spray into the air and make brave people reconsider their life choices in real time. But shoals, reefs, rocky ledges and rapidly changing bottom depth are often the hidden part of the same disaster. They are the lake's quiet contribution to a bad day, and like most quiet contributions to a bad day, they tend to become obvious only after things have already gone wrong. A ship in open deep water has one set of problems. A ship in heavy weather approaching shallow water, rocky structure, or a badly timed harbour entrance has another. The first is mostly about what the sky and surface are doing. The second is about what the lake bottom starts doing to the water from underneath. NOAA's coastal education material explains that as wind-driven waves approach shore, friction between the seafloor and the moving water makes the waves steeper. As different parts of a wave encounter shallower bottom and coastal features, the wave slows unevenly, bends and changes shape. In plain language, the same wave that was already dangerous offshore can become sharper, less forgiving, and more chaotic once bottom depth begins interfering with it. NOAA's Coast Pilot guidance adds an even harder rule. Waves moving into shallow water become steeper and break when the depth is about 1.3 times the wave height. That is a very efficient way for a lake to turn trouble into impact. This is one of the main reasons shoals matter so much. A shoal does not need to be visible to be effective. It only needs to rise high enough toward the surface to change what the water above it is doing. In calm weather, that may mean a navigational hazard, a chart note, or an awkward correction in course. In bad weather, it means the wave field itself starts changing over the top of that hidden rise. The water shortens, steepens, breaks earlier, or piles in awkward ways that can punish a hull, a rudder, or a captain's remaining patience. There is a reason NOAA nautical charts use blue tint to accentuate shoals and other areas considered dangerous for navigation, and there is a reason Coast Pilot warns mariners to inspect those depth contours carefully rather than treating the chart as decorative. The map is already trying to be polite about where the hidden trouble lives. The Great Lakes have a great many of these hidden places. Coast Pilot 6, NOAA's navigation reference for the Great Lakes, is full of lines that read less like scenic description and more like repeated reminders not to become overconfident. On Lake Superior, Whitefish Bay alone includes a rocky ledge extending about 2 miles north from Nodaway Point, shoals that extend about 0.4 mile offshore in the east part of Pendle's Bay, and up to 1 mile offshore farther northwest, and from Salt Point west to Naomi Kong Point, shoals extending 2 miles from shore before continuing across the mouth of Taquamenon Bay. That is not one isolated hazard. That is an underwater geometry problem spread across miles of coastline. On a clean summer day, it might simply be a matter of navigation and local knowledge. In heavy weather, it becomes part of how the lake hurts you. Lake Michigan tells the same story in a slightly different voice. NOAA's Coast Pilot describes White Shoal as about 2 miles long with its west end awash, plus nearby 18-foot shoals and surrounding 20 to 30-foot spots. Simmons Reef, about 5 miles northwest of White Shoal, is described as a large reef with a rock awash near its centre and depths of 3 to 6 feet scattered over a broad area, dangerous because it is made of boulders that make up quickly from deep water. Fagan Reef nearby stretches roughly 4 miles by 2 miles and contains numerous shoal spots less than 24 feet, with a least depth of 10 feet. Grays, Reef is an extensive area of shallow water over rocks extending 8.5 miles, with depths ranging from rocks awash to 18 feet, and the main route through Gray's Reef Passage is literally a dredged channel between hazards with least depths in the teens. None of that sounds like an inland puddle, it sounds like a place where the bottom is waiting for mistakes. Lake Huron is no kinder. NOAA's coast pilot notes Tobin Reef, Pomeroy Reef, and Martin Reef in sequence, with Martin Reef carrying a least depth of 1 foot. Elsewhere along the lake, Holdridge Shoal, Horseshoe Reef, detached 4-foot and 6-foot shoals, rocky ledges and shoal-bordered coves keep appearing in the descriptions. These are not odd curiosities left over from some old survey. They are part of the basic shape of the place. The Great Lakes were carved and filled and reworked over very long periods, and the result is not a nice consistent basin with every dangerous spot helpfully announced in advance. It is a working navigation system full of underwater features that force ships into channels, routes, passages, and margins. Once a storm begins narrowing those margins, the bottom starts feeling a lot less theoretical, and it is worth stressing that charted does not mean trivial. NOAA's hydrographic survey specifications say survey data, update charts and models, fill in bathymetric gaps, and identify dangers to navigation. The same specifications say all features with depths of 20 metres or less in navigable waters may be considered potential dangers to navigation and subject to reporting. NOAA's Great Lakes survey work exists for the safety of navigation precisely because the seafloor matters to commerce and route planning. That is a useful corrective to the idea that modern ships have somehow outgrown this problem. They have not. The whole point of continuing hydrographic survey work is that underwater hazards remain operationally important. A ship may have radar, GPS, electronic charting, and a bridge full of electronics, but if the bottom comes up where you did not expect it, or if the water level has changed more than your margin allowed, the lake is not impressed by your equipment list. The US Coast Guard's navigation guidance adds another uncomfortable detail. The aids to navigation system is not intended to identify every shoal or obstruction that exists in navigable waters. Its primary objective is to mark navigable channels, adjacent obstructions and obstructions in general navigation areas that may not be anticipated, but other waters, even if navigable, are generally not marked. That matters because people often speak as if buoys and lights have solved the underwater problem. They have not solved it. They have managed part of it. The prudent mariner is still expected to navigate with charts, local knowledge, depth awareness, and some respect for the possibility that not every danger has been individually gift-wrapped, with a buoy and a reassuring blink. Then there is the practical matter of dredged channels. The US Army Corps of Engineers maintains the Great Lakes navigation system by dredging channels and harbours, and by constructing and maintaining coastal infrastructure. That one sentence tells you a lot. If channels must be dredged and maintained for the system to function, then the natural condition of many approaches, harbours and routes is not automatically generous to deep draft traffic. A lake freighter is not just wandering through open water and politely arriving at a port. It is often following a managed path through a basin that includes shoals, bars, harbour mouths, and depth limitations that need continual work to remain dependable. In good conditions, that is a logistics issue. In bad conditions, it becomes a survival issue because the safer route may also be the narrower one, and the narrower one may be exactly where steepening waves and cross effects become hardest to handle. Water level makes all of this even less friendly. The Great Lakes are considered non-tidal in the ordinary sense, but NOAA notes that true lunar and solar tides are tiny there and are masked by larger water level fluctuations produced by wind and barometric pressure changes. NOAA also explains that Great Lakes charting uses low water datum, a reference surface so low that water level will seldom fall below it, and that different lakes use different LWD surfaces. In other words, every charted depth is being referenced against a standard designed for safe navigation, but actual lake level still moves above and around that reference due to season, weather, and short-term events. NOAA adds that Great Lakes water levels have long-term, annual and short-term variations, and Coast Pilot for Lake Superior notes that storm-related water level changes can be significant, including an unusually severe storm in 1905 that temporarily raised the water level at Duluth by 2.3 feet. A couple of feet may not sound dramatic until you are discussing underkeel clearance near rock in heavy weather, while a long vessel is already pitching and heaving. Then it becomes the sort of detail people remember. Seiches make that picture even stranger. NOAA explains that seiches are standing wave oscillations usually limited to partially or fully enclosed basins such as Lake Erie, and the National Park Service notes that on the Great Lakes they are typically caused when strong winds and rapid pressure changes pile water up at one end of a lake and then send it surging back once the wind eases. So the bottom hazard is not fixed only in the charted sense. The effective water above it can shift around under meteorological forcing. A harbour or shoreline that was merely awkward can become shallower, rougher, or more strongly affected by water level swings in a matter of hours. That is another way the hidden teeth below get involved. They do not move, but the water over them does, and it does not always move in ways that are kind to anyone trying to enter a refuge in rough weather. This is also why so many dangerous stretches of the Great Lakes earned reputations that lasted. Thunder Bay National Marine Sanctuary says the area sits beside one of the most treacherous stretches of water in the system, where unpredictable weather, murky fog banks, sudden gales, and rocky shoals earned the name Shipwreck Alley. NOAA's sanctuary material adds that North Point Reef, Middle Island and Black River are examples of ship traps that claimed numerous vessels, and that these areas remain unnavigable to modern vessels because shallow rocky conditions make them too dangerous even for research vessels to survey easily. That is a useful phrase, ship traps, because it admits something people often resist. A dangerous piece of water is not always only dangerous because the weather was bad. Sometimes the geography is waiting for the weather to make itself useful. Once you combine all of that with the short period wave behaviour we talked about earlier, the effect becomes fairly easy to picture and fairly unpleasant to imagine. A vessel in deep water may already be dealing with steep, closely spaced waves. As it approaches shallower regions, reefs or shoals, those same waves begin to steepen further because bottom friction slows them and changes their shape. Different parts of the wave field bend according to seabed and shoreline geometry. Breaking becomes more likely as depth decreases. The deck is still taking water, the hull is still being loaded, the crew is still trying to read conditions that are now being altered from below as well as above. A route that looked like refuge on the chart can become a place where wave shape is worse, manoeuvring room is smaller, and the cost of even slight navigational error rises quickly. The lake is no longer only hitting the ship, it is reshaping the water under the ship in real time. There's also a cruel asymmetry to rocky shoals and reefs. Deep water is often forgiving of small navigational imprecision. Shallow rocky structure is not. NOAAs. Coast Pilot entries are full of details like least depth 12 feet, rock awash, shoals extend 2 miles from shore, or dangerous because it is composed of boulders that make up quickly from deep water. That last phrase is especially nasty because it means the bottom does not always rise gradually enough to give much natural warning. One moment you have ample water. The next moment the chart is telling you there are boulders and awash rock, where you really would have preferred more polite geology. In calm weather, that is an argument for precise navigation. In storm weather, with a vessel yawing and rolling and taking repeated sea loads, it becomes one more way the margin can collapse. So when people say the Great Lakes can break ships in half, it is not only the sky doing the work. The bottom helps, the reefs help, the shoals help, the rocky ledges, the narrow dredged passages, the shifting water levels, and the waves steepening over shallows all help in the most unhelpful way possible. The lake first uses wind to build the sea state, and then, when a vessel gets too near the wrong underwater shape, it starts sharpening that sea state with the basin itself. It is a bit like discovering that the floor has joined the fight after you were already busy with the ceiling. And once the water is coming aboard and once the ship is being bent, pounded and handled in that kind of terrain, the next problem is not simply where the rocks are. It is what repeated load and uneven support begin doing to the steel itself. Because long before a ship fails outright, the hull has usually been giving warnings in the only language a structure really has. A ship looks solid when you see it from shore. That is part of the illusion. It is steel, riveted or welded into something enormous, layered with decks, bulkheads, frames, girders, machinery, cargo spaces, railings, pipes, ladders, and enough weight to make it seem more like a moving building than a floating object. But a ship's hull is not meant to be perfectly rigid. It cannot be. Classification rules treat it as a hull girder, essentially a very long beam that is constantly being bent by its own weight, its cargo, the still water supporting it, and the waves changing that support from moment to moment. The International Association of Classification Societies requires ships of sufficient length to be checked for both hogging and sagging load cases, and it defines hull girder ultimate bending capacity as the maximum bending moment capacity, beyond which the hull structure collapses. That is the polite engineering way of saying there is a limit, and once the sea and the ship's own loads push past that limit, the structure stops coping and starts failing. That limit matters, because the sea does not support a ship evenly. In calm water, the upward buoyant force along the hull is already not identical at every point, but in waves the support pattern becomes much more dramatic. Lloyd's Register explains the two classic bending conditions. In hogging, the ship is more strongly supported around the middle, so the hull arches upward there. In sagging, the ends are better supported than the middle, so the hull droops. IACS rules build directly around those same two cases because they are not rare curiosities. They are normal structural states. Ships are expected to survive. The trouble begins when wave-induced bending moments combine with still water bending moments, cargo distribution, local damage, and repeated impacts until normal structural state starts drifting toward ultimate capacity. That is why a hull does not usually fail like a snapped twig. Failure begins more quietly. The steel is stressed. The deck is in tension or compression depending on the bending state. The bottom structure is taking the opposite pattern. Hatch coamings, plate panels, stiffeners, and welded connections all become part of a very large argument about load paths. IACS rules specifically call for bending strength checks at the bottom, at the deck, at the top of hatch coamings, and at points where steel yields strength changes, and they also require buckling checks for plate panels and longitudinal stiffeners, subject to hull girder bending and shear stresses. That tells you exactly where engineers expect trouble to begin. Not in some magical single point, but in the parts of the hull that are repeatedly asked to carry global loads while also enduring local ones. Buckling is one of those terms that sounds academic until you picture what it means. It does not necessarily mean the whole ship folds in half all at once. It means a structural element in compression loses stability and starts deforming in a way it was not supposed to. Plates can buckle, stiffeners can buckle, local panels can give first, which then alters how neighbouring structure carries load. IACS rules describe failure limit states for elementary plate panels, overall stiffened panels, and longitudinal stiffeners, and they include buckling utilisation checks because hull failure is often progressive. The structure may not go from perfect to gone in a single instant. It may go from intact to overstressed, from overstressed to locally unstable, and from locally unstable to rapidly worsening as load redistributes into already unhappy neighbouring steel. This is where wave timing becomes so nasty. In the previous section, we looked at short-period Great Lakes waves arriving in quick succession. Structurally, that means the hull is not simply taking one large bend and then relaxing. It is cycling through stress states again and again. The US Ship Structure Committee's fatigue guide says the service life of a ship can be divided into a teething phase, where fatigue cracks initiate from fabrication defects, a stable phase, and then an aging phase in which the rate of fatigue cracking rises because of cumulative fatigue damage and other structural degradations such as wear and corrosion. The same guide notes that the rate of reported fatigue cracking and other structural failures increases significantly after the first 10 years of service. In other words, steel does not merely endure load, it remembers load, and that memory accumulates. That accumulation is one of the reasons a ship can look sound right up until it is not. Fatigue is rarely theatrical in its early life. A crack begins where the geometry is unfavourable, the weld detail is imperfect, the local stress concentration is high, or the steel has already been nicked by service. The same Ship Structure Committee guide explains that fatigue cracks can initiate from fabrication defects, and that damage-tolerant design is supposed to give ships enough residual strength to survive until damage is detected and repaired. That is an important phrase, until damage is detected and repaired, because it implies something uncomfortably human. The structure may be trying to announce a problem for quite some time, but the announcement only helps if somebody notices it and takes it seriously. Unfortunately, ships are very good at creating exactly the kinds of places where cracks like to begin. The Transportation Safety Board of Canada's investigation into the Lake Carling fracture is unusually clear on that point. It identified stress concentration factors at the lower ends of some side frames, including discontinuities caused by scallops or cutouts in the frame, proximity to a shell plate seam, change in plate thickness at the seam weld, and residual stresses in restrained welded connections. The report concluded that these conditions helped create small initial cracks. That is a very useful lesson because it shows how failure starts in ordinary shipbuilding realities. A cutout here, a weld there, a thickness transition nearby, a repaired area perhaps not as perfect as everyone hoped. None of these details is dramatic on its own. Together, under cyclic load, they become where the hull begins negotiating with damage. Openings complicate the problem further. The hull girder of a ship is only as strong as the section it actually has, not the section people vaguely imagine it has. IRCS survey criteria say that when calculating the transverse section modulus of the hull girder, the area of all continuous longitudinal strength members must be taken into account, and large openings must always be deducted from the sectional areas used in the calculation. That is not an abstract bookkeeping exercise. It is a reminder that holes, hatch openings, cutouts and deducted areas reduce the amount of structure available to resist bending. On Great Lakes bulk carriers, where large cargo hatches are central to the whole design, that fact matters. A long ship carrying bulk cargo is efficient because of those large hold openings. Structurally, though, every opening is also something that must be accounted for, because it interrupts the cleanest possible load path through the deck region. Corrosion makes the conversation worse because it quietly changes the ship you think you have into a thinner ship than the one that was launched. ERCS hull. Survey requirements for older ships explicitly evaluate longitudinal strength using thicknesses measured during special surveys. The rules say that if diminution of the deck or bottom flange sectional areas exceeds 10% of the as-built area, renewal, reinforcement or recalculation is required, and that the actual transverse section modulus for ships under those rules is not to be less than 90% of the required section modulus for new buildings. Those numbers are not there for decoration. They are there because loss of thickness means loss of strength, and loss of strength means less margin when the sea starts applying the same old loads to a now smaller effective section. The fatigue guide says much the same thing in a different voice. It notes that general and localized corrosion increase cyclic stresses by reducing net section and stiffness, and that corrosion can accelerate both the initiation and propagation of fatigue cracks. It also notes that stress cycling promotes corrosion, and corrosion accelerates crack formation, which is a rather miserable partnership. A crack-prone area becomes coating-prone in the wrong way. A corroded area becomes stress-prone in the wrong way. And all of it tends to happen in the same places ships already dislike. Details, joints, stiffener terminations, corners, and connections where the geometry is asking the steel for a little more than steel likes to give. Cold makes everything more serious. Steel that is perfectly adequate under one temperature regime can behave much less forgivingly near or below freezing if toughness is insufficient. The Transportation Safety Board of Canada's Lake Carling report explains that low temperatures tend to reduce steel's ability to resist crack growth, and warns that residual risks for unstable brittle fracture remain present in vessels built with some Grade A and B steels, especially in colder climates. The report also states that ships, especially bulk carriers, operating in cold waters and having sideshell material with characteristics similar to the Lake Carling are at risk, because damage tolerance could be less than adequate and cracks could remain unnoticed or be discounted as insignificant. That is a deeply unhelpful combination. A crack too small to alarm someone, in steel too cold to arrest it once it matters. This is where people often imagine a hull failure as one dramatic overload event, as though a single wave simply proves stronger than steel, and that was that. Sometimes a single extreme load can be decisive, but even then it often arrives at the end of a longer story. The story usually includes accumulated fatigue, local defects, corrosion wastage, residual stresses, repeated bending, and perhaps loading or service events that have already consumed part of the structure's life. The Lake Carling investigation found that service loads greater than those approved for the vessel likely contributed to crack formation. The fatigue guide, meanwhile, describes a ship's service life as something that moves through stages of worsening crack susceptibility. So when a storm finally seems to break a hull, the storm may actually be the last sentence in a much longer paragraph the steel has been writing for years. And then there is the difference between yielding and fracture. Yielding is what happens when the steel is pushed beyond its elastic range and deforms permanently. Fracture is what happens when the material actually tears or separates. A hull may yield locally and still survive. It may buckle locally and still survive. It may crack and still survive for a time. The IACS framework reflects that layered reality by checking yielding, shear, buckling, and ultimate hull girder capacity separately. A ship does not need to jump straight from healthy to split in two. It can first enter a condition in which local damage, distortion, or crack growth erodes the structure's ability to absorb the next load. Once enough of that reserve is gone, the next severe bend, slam, or flooding event can push the hull into collapse. The Edmund Fitzgerald remains the most famous Great Lakes example of how ugly this sequence can become, even if the exact final mechanics are still debated. The National Transportation Safety Board concluded that the probable cause was sudden massive flooding of the cargo hold due to the collapse of one or more hatch covers. Before the hatch covers collapsed, the board found that flooding into ballast tanks and the tunnel through topside damage, together with flooding into the cargo hold through non-weathertight hatch covers, reduced freeboard and increased list. Hydrostatic and hydrodynamic forces on the hatches then exceeded their capacity. That conclusion matters because it shows a real ship loss in which structural failure was not a neat, clean snap caused by one wave alone. It was a combined failure involving damage, water ingress, reduced freeboard, worsening sea loads, and then a critical structural element giving way. That pattern is worth lingering on because it corrects a common misunderstanding. When people say the Great Lakes can break ships in half, they often picture a vessel being bent once dramatically, until it parts like a biscuit. Real structural failure is often less tidy, and therefore more frightening. Water comes aboard. A list develops, freeboard reduces, waves now strike lower and more often. Hatch covers, coamings, deck plating and side structures are being asked to endure loads they were never meant to take in that condition. The hull girder is still bending globally, while local structures are already compromised. A crack that might once have been tolerable becomes dangerous because the surrounding structure is wetter, colder, thinner, or more distorted than before. The system begins to fail as a system. There is also something grimly practical about how classification rules are written that helps explain this. They are not written as though ships are indestructible. They are written as though ships are always balancing capacity against load, and as though both sides of that balance can change. Loads change with sea state, speed, heading and cargo condition. Capacity changes with corrosion, damage, cracks, repairs, temperature and age. IACS rules explicitly require assessment of hull girder ultimate strength and state that capacity beyond a certain maximum bending moment is where the structure collapses. Survey rules explicitly require measured thicknesses and strength re-evaluation in older ships. Those are not the habits of an industry that believes steel is simply strong enough by default. They are the habits of an industry that knows steel has to keep proving itself. What makes the Great Lakes such a sharp setting for this story is that they provide the right kind of punishment. The waves are often steep and closely spaced. The weather can change quickly. The water is cold enough to make brittle behaviour more concerning and rescue less forgiving. Ships may be heavily loaded with dense bulk cargoes. Routes may bring them near shoals, harbour approaches, or restricted passages when the sea is already hard on the hull. In that environment, steel failure is rarely about one villain. It is about interaction. The global bending loads, the local stress concentrations, the corrosion losses, the fatigue history, the cold, and the water on deck all begin collaborating in the least charming way imaginable. So a hull begins to fail quietly, then mechanically, then all at once. It begins in geometry, in welds, in cutouts, in corrosion scars, in unnoticed cracks, in load cycles that seem manageable one voyage at a time. It continues in repeated hogging and sagging, in yielding and buckling, in section loss, in reduced toughness, in the bad luck of cold and heavy seas arriving together. And when the visible failure finally comes, with plates tearing, hatches collapsing, or the hull girder losing its ability to carry load, the ship is no longer just fighting the lake as a surface. It is fighting the weight and motion of water, now entering places it should never have been allowed to enter, which is where the structure's remaining margin starts disappearing even faster. Once the lake starts putting water on the ship instead of under it, the whole problem changes. Up to that point, the vessel is still mainly dealing with external force. The waves are lifting, dropping, and bending the hull from outside. The wind is pushing from above. The ship is still in a fight with the environment, but the environment remains, in a technical sense, outside the structure. The moment water begins coming over the deck and staying there, or entering spaces where it was never supposed to be, the lake stops acting only like weather and starts acting like unwanted cargo. That is where a rough passage can become a deadly one. The US Coast Guard stability guidance says water on deck from boarding seas creates a significant loss in overall stability from 3 negative impacts at once: weight added high, lower freeboards, and free surface. In one sentence, that gives you the shape of the problem. The ship is not merely being hit by water, it is being changed by it. That added weight matters more than many people realise because deck water is badly placed weight. The Coast Guard's Quick Stability Guide states the general rule very plainly. Keeping weight low helps stability, while adding weight high raises the centre of gravity and makes a vessel more susceptible to capsizing. When waves sweep over the weather deck, the ship is suddenly carrying water in one of the least helpful places possible, and unlike ballast loaded deliberately into tanks, this water has not arrived as part of some calm, controlled stability plan. It has arrived violently, unevenly, and in conditions where the next sea is already on its way. A few tons of water carried low in a proper tank can be useful. A few tons of water spread and sloshing over a working deck in heavy seas are another matter entirely. They reduce reserve safety exactly when reserve safety is most needed. The next problem is lower freeboard. Freeboard is simply the distance between the waterline and the deck edge, but in bad weather that distance is also time, margin and forgiveness. More freeboard means the lake has to work harder to keep getting on deck. Less freeboard means boarding seas come aboard more easily and more often. The Fitzgerald investigation letters from the NTSB say, that because amendments to the Great Lakes load line regulations allowed the Fitzgerald's minimum freeboard to be reduced, greater amounts of water washed over the deck from boarding seas. The same analysis said this increased the rate at which flooding water entered damaged ballast tanks, the tunnel, and the cargo hold, which further reduced freeboard and increased list until boarding seas caused failure of one or more hatch covers. That is the ugly feedback loop in its pure form. Water comes aboard because the ship is low enough. The extra water makes the ship sit and behave worse. Because it sits and behaves worse, still more water comes aboard. That loop becomes even more dangerous because water that remains free to move creates what mariners call free surface effect. The Coast Guard guide explains that free surface occurs when liquids in slack tanks, flooded bilges, fish holds, or other spaces shift to the low side as the vessel heels. That shift moves the liquid's centre of gravity outward, which in turn shifts the vessel's effective centre of gravity outward and reduces the righting arm. The Coast Guard also says slack tanks, water in holds, or flooded bilges can significantly reduce overall stability, and that this reduction is larger for very wide compartments spanning the full beam than for narrow tanks. In plain language, if the ship heels and the water inside it or on it runs to the low side, the water helps the heel instead of helping the recovery. The vessel still has buoyancy, but its ability to right itself has been quietly weakened by the motion of the water it has trapped. This is one of the reasons water on deck is not just about the simple weight of a wave. It is about mobile weight. A boarding sea that lands and then immediately drains away is bad enough. Water that lands, lingers, and then shifts across the beam as the ship rolls is worse. The Coast Guard's quick card is so blunt about this that it turns the advice into almost a shouted command. Do not permit water to collect on your deck and keep your freeing ports open. That sounds like common sense, and it is, but it also reveals how seriously naval and regulatory thinking treats trapped deck water. Water on deck is not considered a minor nuisance to be dealt with when convenient. It is a recognised stability hazard. Once enough of it remains aboard, the ship is no longer only being struck by the sea, it is carrying part of the sea with its own centre of gravity in all the wrong places. Freeing ports are therefore not decorative cutouts in the bulwarks. They are part of the vessel's survival system. The IMO Intact Stability Code says freeing ports, open rails, and scuppers must be fitted as necessary for rapidly clearing the weather deck of water under all weather conditions. The same code stresses that where bulwarks form wells, freeing ports should be arranged along their length, so the deck is freed of water most rapidly and effectively, with their lower edges as near the deck as practicable. It even warns that gear, boards, or stowage arrangements must not trap water on deck or impair the effectiveness of the freeing ports. That is a very direct acknowledgement that drainage is not an afterthought. It is the difference between a wave passing over the ship and a wave becoming part of the ship's instability problem. If those drainage paths are blocked, iced up, badly arranged, or simply overwhelmed by the amount of water coming aboard, the deck turns into a shallow, shifting load basin, and the sea does not have to break a hatch cover immediately for the danger to become serious. The Coast Guard Stability Guide notes that progressive downflooding causes a reduction in overall stability over time, and warns that when the downflooding is caused by a slow leak, the effect may not be noticeable at first until the vessel has already suffered a dangerous reduction in stability. That is a useful point because ship losses are often imagined as dramatic all-at-once events. In reality, a vessel may begin the terminal part of its voyage in a much quieter way. A vent is damaged. A hatch is not as weather-tight as it should be. Spray finds a gap. Water enters a tank, a tunnel, a bilge, or a hold. The amount is not yet enough to trigger instant panic, but it is enough to begin altering list, trim, freeboard, and the righting curve. By the time the crew feels or sees the full effect, the ship may already be significantly worse off than anyone realised. That is exactly why the Fitzgerald remains so instructive. The NTSB did not conclude that one giant wave simply smashed the ship flat in a single heroic moment. It concluded that the probable cause was sudden massive flooding of the cargo hold due to the collapse of one or more hatch covers. Before that collapse, the board said flooding into ballast tanks and the tunnel through topside damage, along with flooding into the cargo hold through non-weather tight hatch covers, had already caused reduced freeboard and a list. Only then did the hydrostatic and hydrodynamic forces from heavy boarding seas at that reduced freeboard, and with that list cause the hatch covers to collapse. That sequence matters. Water first weakened the ship's condition, then heavier seas exploited that weakened condition. Then the final flooding became catastrophic. The lake did not need one theatrical blow. It needed successive compounding ones. Once water gets into a hold, the problem becomes larger than the opening that admitted it. The NTSB recommendation letter on the Fitzgerald notes that Great Lakes bulk cargo vessels like her were not required to meet subdivision or damage stability standards such that flooding of one cargo hold could be safely contained. It states that flooding of one cargo hold would have propagated throughout all cargo holds and eventually could have led to the sinking of the vessel, and that if the Fitzgerald had been designed to withstand flooding of one cargo hold, the chances for vessel or crew survival would have improved. That is a deeply serious design lesson. A ship that cannot localise flooding is a ship in which one successful water entry point can begin turning a section problem into a ship-wide problem. It is the maritime equivalent of a small leak discovering there are no interior doors worth trusting. There is also the matter of how water inside a hold interacts with trim and pumping. The same NTSB letter notes that the Fitzgerald had no means of detecting water in the cargo holds other than visual inspection, and no means of dewatering the cargo hold if flooding occurred in the forward hold. It also said flooding in the forward hold would have caused trim by the bow, and that by the time enough water had entered the cargo holds for the bilge systems to be used, the vessel might already have been in danger of sinking. That is a brutal practical problem. Water entering a forward hold does not politely wait for the crew to finish diagnosing it. It pulls the bow down, lowers forward freeboard, makes it easier for the next seas to board over the front, and can reduce the crew's ability to inspect and correct the situation in time. A little water forward can therefore become an argument for a lot more water forward. Now add cargo to this picture. Bulk cargo ships are designed to carry dense loads efficiently in large holds under large hatch openings. That's the whole point of the type. But a flooded bulk hold is not just a tank. It is a cargo space containing water, cargo, structure and air, in combinations the designer never intended during normal service. The Coast Guard's stability rules and guidance treat partially filled spaces seriously, because wide free surfaces are especially harmful. A long broad hold with water moving inside it is an ugly stability feature, even if the cargo itself does not liquefy or shift in the dramatic way some cargoes can. The hold still contains a free-moving body of water that can slosh, change, trim, and reduce righting energy. If the cargo does shift as well, or if water penetrates through several holds, the ship is now carrying an unstable internal load. It cannot simply throw over the side or drain quickly enough to restore its former condition. There is another, less obvious danger in all this. Water aboard increases not only total weight, but also the way loads are distributed along the hull. Water trapped on deck forward, or flooding concentrated in a forward hold, changes the bending picture of the ship. The hull girder is still dealing with the sea outside, but now it is also dealing with altered internal loading. In the Fitzgerald findings, flooding in the ballast tanks, tunnel and cargo hold was already enough to reduce freeboard and increase list before the hatch cover collapse. That means the ship's external and internal problems were already interacting. Water was coming from outside, but once aboard it was altering the ship's geometry in the sea. The bow could ride lower, the deck could ship more water, and each new boarding sea would arrive against a vessel with less reserve and a worse attitude to the waves than before. That is how flooding turns from a stability issue into a structural multiplier. The hatch covers sit directly in the middle of this story because they are the border guards between deck seas and cargo spaces. The IMO load lines rules require hatch covers in exposed positions to be of steel, or equivalent material, to be weather-tight, to have gaskets and clamping devices, and to maintain that tightness in any sea conditions. The rules also specify minimum design wave loads for hatch covers, depending on the ship's length and location of the hatch. That regulatory detail tells you something important. Hatch covers are not expected merely to keep out rain. They are expected to endure very real wave loads. If a cover is weakened, badly maintained, not fully weathertight, or subjected to conditions beyond what its actual condition can handle, the line between shipped water and hold flooding can disappear very quickly. And once that line goes, the ship has likely moved into a much more dangerous category of casualty. This is why boarding seas is not just an atmospheric phrase old mariners use to sound experienced. In the Fitzgerald record, it is the operative mechanism by which the deck kept being loaded, flooding rates increased, and the final failure sequence advanced. The NTSB described heavy boarding seas acting on the hatch covers after previous flooding had already reduced freeboard and increased list. That means the water on deck was no longer a secondary discomfort. It was part of the direct force being applied to a critical structural closure. The ship was effectively offering the storm a lower, more vulnerable target every time the condition worsened. Once the hatch covers failed, the cargo hold no longer had any real defence against rapid flooding, and the rest of the ship's reserve life would have been measured in very little time at all. There is something especially cruel about how ordinary this can begin. A bit of water on deck, a little ingress through a closure not as tight as everyone hoped, a slight list, a little trim by the bow, a little less freeboard than before. None of those phrases sounds dramatic by itself. But the Coast Guard's guidance is explicit that water on deck harms stability through added high weight, lower freeboard, and free surface, while progressive downflooding can erode stability gradually until the reduction becomes dangerous. Read together, those points describe a ship being slowly prepared for its own worsening. The deck becomes easier to flood, the flooding becomes easier to retain, the retained water makes the vessel less able to resist the next wave, and the next wave becomes more likely to force water deeper into the ship. It is not one failure, it is a staircase, and that is why the weight of water is so deadly. It is not deadly only because water is heavy, though it is. It is deadly because it arrives in the wrong place, moves at the wrong time, drains too slowly, lowers the ship, reduces the righting arm, finds openings, worsens trim, and can turn exposed deck structures into failed boundaries. The sea beneath the hull may be violent, but it is still where a ship is supposed to meet water. The real trouble begins when the lake steps onto the weather deck, settles there, and then starts looking for the next opening down. By then, the vessel is no longer just riding the storm, it is carrying part of the storm inside itself, and that is usually the point where steel, stability and time all begin running out together. The next part of the story follows that danger into real storms and real losses, because once all these mechanics are in place, the Great Lakes do not need to prove their reputation in theory anymore. They have already done it in the names mariners still remember. There is a point when you spend enough time reading about the Great Lakes, when the wrecks stop feeling like isolated tragedies and start feeling like a conversation the water has been having for a very long time. Certain storms come up again and again, not because people on the lakes enjoy retelling misery for its own sake, but because those storms taught the same lesson with such force that no one quite forgot it afterward. The names change, the ships change, wooden hulls give way to steel freighters, forecasting improves, radios improve, navigation improves, yet the same broad pattern returns. A lake that looked survivable turns hard. A wind that sounded manageable finds a long fetch. Waves build into steep, punishing seas. Water gets where it should not. A ship loses margin one step at a time, and then all at once. That is why some storms become legend. They are not just weather events. They are moments when the lakes explain themselves in the bluntest possible terms. Thunder Bay in Lake Huron is one of the clearest places to see how geography and memory pile up together. NOAA says the sanctuary area off northeastern Michigan sits beside one of the most treacherous stretches of water in the Great Lakes system, where unpredictable weather, fog, sudden gales and rocky shoals earned the nickname Shipwreck Alley. Thunder Bay National Marine Sanctuary now protects nearly 100 known historic shipwrecks within its boundaries, while NOAA's Ocean Service says historical research suggests more than 200 wrecks may rest in the wider area. That concentration is not an accident of storytelling. It is what happens when busy shipping lanes, bad visibility, sudden storms and underwater hazards spend generations working in combination. The wrecks are history, certainly, but they are also evidence. One of the earliest storms that deserves to be called legendary came in 1905, and it is useful precisely because it shows that the lakes did not need modern steel giants before they learned how to be lethal. NOAA's Thunder Bay page on the Joseph S. Fay says the freighter left Escanaba on October 19, 1905, in calm, clear weather, towing the barge DP Rhodes and loaded with iron ore. Then the weather changed dramatically. Winds exceeded 60 miles an hour, the ship struggled to hold course, the towline had to be cut, and after one massive wave washed the mate overboard, the rest of the crew escaped in a lifeboat while the vessel sank. There is something almost offensively familiar about that sequence. Calm departure, heavy cargo, weather deterioration, loss of steering control, wave damage, abandonment. It reads like a template the lakes would continue reusing. The details differ from case to case, but the shape of the danger is already there. The same year produced another wreck that feels almost too on the nose for the subject we have been exploring. NOAA's Mariners. Weatherlog recounts what happened to the Matafa during the November 27th, 1905, gale on Lake Superior. Snow, ice pellets, freezing temperatures, and what the article calls mountainous seas spread havoc over the lake. The ore-laden freighter tried to turn back for shelter after battling the storm, but while attempting the harbour entry, she was caught by the current, pushed off course, hit bottom, smashed the pier, lost power, and was driven aground and broken into 3 pieces. 9 men on the stern died of exposure after the boilers went out. That wreck matters because it ties together nearly every ugly factor in our story so far. Wind built the sea, current complicated the approach, the harbour did not behave like safety simply because it was near land. Bottom contact joined the punishment already being delivered by the storm, and once the hull was no longer whole, the cold finished what the waves had started. Then came the November 1913 storm, the one that sits at the centre of Great Lakes weather memory like a scar. The National Weather Service says the storm of November 7th to 10th, 1913, nicknamed the White Hurricane, remains the largest inland maritime disaster in US history by number of ships lost. Its retrospective material says more than 250 lives were lost at sea, at least 12 ships sank, and at least 30 more were driven ashore, crippled or destroyed. The storm combined blizzard conditions with hurricane-force winds, and NOAA's NWS article says mariners endured winds around 90 miles per hour and waves reaching 35 feet, with whiteout conditions and icing making an already dangerous situation deadlier by wrecking navigation. This is the storm that turned the phrase November gales from a seasonal nuisance into a warning with historical weight behind it. It is worth slowing down here, because the White Hurricane shows why legend is sometimes just a practical word for repeated disaster at exceptional scale. According to the NWS retrospective, the storm intensified as 2 low-pressure centres merged over the Great Lakes, with storm-force winds persisting over 4 days. In 1913, gale warnings were sent by telegraph to shore stations, where volunteers displayed flags and lanterns, but vessels once beyond sight of land had no way to learn that the storm had become much worse than expected. Even forecasters were caught off guard by its strength and longevity. So the ships already out there were not just battling high seas, they were battling them in a communication age that offered much less help once the weather stopped cooperating. That is one reason 1913 still stands apart. The lakes were already dangerous enough, The available tools were simply not equal to what was coming. The list of losses from that storm reads like an inventory taken after some industrial nightmare. NWS retrospective material names the John A. McGean, Isaac M. Scott, Plymouth, Charles S. Price, Henry B. Smith, Argus, Hydrus, Leafield, Regina, and James C. Carruthers among the ships lost, with many of the sinkings concentrated in the evening of November 9th into the early hours of November 10th. 8 ships and 187 lives were lost during that window alone, according to the retrospective. Most of those vessels did not sink in a leisurely way that allowed posterity a neat official closing statement. Some vanished outright. Some were found later. Some remained mysteries for decades. The storm did not merely destroy hulls, it erased explanations. Among the 1913 losses, the Isaac M. Scott has a particularly grim place in the record. NOAA's Thunder Bay Sanctuary says the 524-foot steel freighter was lost on November 10, 1913, carrying coal, and the NWS White Hurricane article identifies her as one of the major wrecks in Thunder Bay's shipwreck alley. That combination is instructive. By 1913, the lakes were not only claiming wooden vessels in primitive conditions, they were also taking large steel freighters that represented some of the newer industrial muscle of Great Lakes commerce. The point is not that steel failed because steel was poor, it is that a large lake storm, given enough wind, enough icing, enough wave energy, and enough navigational difficulty could punish even one of the bigger and stronger ships of its day into the bottom. There is nothing quaint about that. The Regina is another 1913 name that lingers because it captures the same broad truth from a different angle. The NWS retrospective lists her among the vessels lost on Lake Huron near Harbour Beach during the storm. In the broader storm accounting, she belongs to a cluster of ships taken in the same general period when Lake Huron became the centre of catastrophe. It is tempting, looking back, to imagine individual shipwreck stories as somehow separate, as though each captain had simply found his own private bad luck. The 1913 record refuses that comfort. These were not isolated errors scattered by chance. They were concentrated losses inside a single weather event, strong enough to overwhelm multiple vessels across a large basin. When too many ships begin disappearing in the same storm, the lakes are no longer asking for respect one voyage at a time. They are demanding it system-wide. The Henry B. Smith adds one more hard detail to that picture. The NWS retrospective lists her as lost on Lake Superior near Marquette on November 9th. For years she remained one of the famous missing ships of the White Hurricane. That matters because mystery tends to enlarge storms in memory, but in this case the mystery was earned. With no survivors and no immediate wreck location, the ship became one of those Great Lakes absences people kept returning to. Even the retrospective notes that because there was no onboard radio communication in 1913, the exact times of many losses can only be estimated. The storm did not just sink ships, it broke the chain of witness. When a lake takes a vessel in heavy weather and leaves nothing but a time window in a probable area, it becomes easier to understand why people around these waters speak with a tone outsiders sometimes mistake for melodrama. And then, as if to make sure no one concluded that the Great Age of Wrecks had ended with better construction, Lake Michigan produced the Carl D. Bradley in 1958. NOAA's Mariner's Weatherlog says the 638-foot steamer, after discharging the last cargo of the season, was heading up Lake Michigan on November 18th, when 60-mile-per-hour winds and towering waves battered the vessel and the hull suddenly cracked. The ship sank in 360 feet of water southwest of Boulder Reef. Only 2 men from the crew of 35 survived. That is a horrifyingly efficient summary, and it is especially relevant to our question because it places structural failure in the middle of a Great Lakes storm, not as folklore, but as documented event. A large steel vessel in November weather was not simply swamped. It suffered catastrophic hull failure. The lake found the ship's margin and went through it. The Bradley also shows why the seasonal timing matters so much in Great Lakes lore. November is not remembered merely because it is cold and unpleasant. It is remembered because it is when warm season assumptions finally give up and the atmosphere starts dealing in stronger gradients deeper systems, and harder water. The NWS says the White Hurricane struck in early November with hurricane-force winds and blizzard conditions, and the Fitzgerald went down in a violent fall storm on November the 10th, 1975. The calendar keeps repeating itself in these stories because late-season storms are where long fetch, unstable air, cold water, and heavily worked vessels begin aligning in the most expensive way possible. It is as though the lakes save some of their sharpest lessons for the point in the year when people are already tired, and commerce would very much like one more trip before winter closes the discussion. That brings us, inevitably, to the Edmund Fitzgerald. The National Weather Service says she departed Superior, Wisconsin on November 9th, 1975, carrying 26,116 long tons of iron ore, and was lost the next day just northwest of Whitefish Point during a violent fall storm. NWS Margate says all 29 crew members were lost, and that the Fitzgerald remains the largest shipwreck on the Great Lakes. The Fitzgerald's place in memory is partly due to size and partly due to timing. By 1975, modern forecasting, communications, and steel shipbuilding were all far ahead of where they had been in 1913. This was not a story from the age of lantern warnings and telegraph flags, and yet the lake still managed to take a 729-foot ore carrier with no survivors. That is why the Fitzgerald remained so central. It denied people the comforting belief that the old disasters belonged only to a rougher, less capable era. The Fitzgerald is also important because the storm around it was not a fairy tale superstorm invented after the fact. NWS Marquette's Fitzgerald pages describe it as a violent November gale, and the wider NWS material on Great Lakes storms places it firmly in the tradition of severe fall weather on Superior. Earlier in our discussion, we looked at the NTSB conclusion that reduced freeboard, flooding, and eventual hatch cover collapse likely drove the final loss. Set beside the historical storm record, that makes the Fitzgerald less of a mysterious one-off, and more of a modern expression of an old Great Lakes pattern. The lake built steep seas, the ship accumulated damage and flooding, margins shrank, the weather kept working. The difference between 1913 and 1975 was not that the lakes had become kinder, it was that they had waited for a newer victim. One thing all these stories have in common is that the ships did not necessarily begin doomed. The Joseph S. sailed in calm, clear weather before conditions changed dramatically. The White Hurricane caught even seasoned captains and weather forecasters by surprise with its intensity. The Bradley had already had hull damage earlier in 1958, then encountered severe November weather at the end of the season. The Fitzgerald sailed into a storm environment that worsened its situation over time. This is worth emphasising because people like disasters that are obvious from the opening scene. Great Lakes losses often are not. They usually begin with a working vessel in a working season, on a route people know, under conditions that are not yet terminal. The lake does not always announce catastrophe with a trumpet. Sometimes it introduces it gradually, then closes the door before anyone has finished the diagnosis. There is another reason these storms live so stubbornly in memory. The wrecks often remain. NOAA says Thunder Bay's cold fresh water preserves shipwrecks exceptionally well, with many sites remaining largely unchanged, and some deeper wrecks functioning almost like time capsules. That preservation gives the losses an afterlife. On an ocean coast, time and salt often shred the evidence more quickly. On the Great Lakes, the victims can remain below in eerie clarity, as if the water is unwilling to stop making its point. A preserved wreck is not just a grave, it is also an argument against complacency. It says in steel and timber and cargo gear still resting on the bottom that this happened here and here and here again. So when people call these storms legendary, the word should not be mistaken for romantic. There is nothing romantic about over 250 dead in 1913, or 33 lost on the Bradley with only 2 survivors, or all 29 men on the Fitzgerald vanishing in modern times. The legend comes from recurrence, from scale, and from the sheer stubbornness with which the same environment keeps proving that fresh water can be every bit as merciless as salt. The lakes earn their stories because they keep producing the conditions that stories are built from: distance, weather, darkness, cold, hidden bottom, and vessels large enough to seem secure right up until they are not. And that is really the point of dwelling on these storms at all, not to turn shipwrecks into theatre, and not to stand admiring tragedy from the comfortable side of a screen, but to notice how often the same ingredients recur: sudden gales, long fetch, steep waves, icing, reduced visibility, shoals, structural strain, flooding, deck water, a lost margin that gets harder to recover with every passing hour. The storms become famous because they are concentrated demonstrations of the forces we've been following all along. They are the lakes taking the theory and writing it in wreckage. And once you have seen that pattern repeated from wooden freighters to steel bulk carriers, the next question becomes even more unsettling, because it is no longer only about old storms and remembered names. It is about why those same lakes can still surprise modern mariners who have better forecasts, stronger ships, and no shortage of historical warnings to study. By this point, it would be easy to assume that modern mariners should have solved the Great Lakes. The ships are better built, the charts are better maintained, the communication is vastly better than it was in 1913, and the weather information is no longer limited to shore flags and educated guesswork. The National Weather Service now provides a broad range of marine forecast and warning products for the Great Lakes in both graphical and text formats, and the official forecast structure includes Great Lakes Open Lake forecast through Day 5, as well as nearshore marine forecast issued 4 times a day, with updates as necessary. On top of that, NOAA runs operational wave guidance for the Great Lakes 4 times a day, with forecasts extending to 84 hours. In other words, modern mariners are not out there blind. They're operating inside a system built around forecasting, warning, and route planning. And yet, the surprise remains. Not because professionals are careless, and not because the forecast system is weak, but because the lakes still produce the sort of conditions that punish confidence faster than confidence can update itself. NOAA's own wave model paper says that despite the common notion that Great Lakes wave conditions are generally benign, intense storms and rapidly changing weather patterns can generate severe sea states that become serious hazards to commercial and recreational vessels. That is an important sentence because it explains the problem in a very modern way. The lakes do not need ignorance in order to be dangerous. They only need variability, speed, and enough scale to turn a reasonable forecast into a difficult real-world sequence of decisions. Part of the surprise comes from how many good tools mariners now have, because good tools can quietly encourage the idea that uncertainty has been domesticated. The Fitzgerald material from Michigan Sea Grant makes the opposite point. It says research after storms like the Fitzgerald improved forecasters' understanding of rapidly deepening low-pressure systems and allowed more accurate and detailed forecasts, while also emphasizing that accurate wind and wave forecasts remain critical both for large freighters and for recreational users. That is a subtle but serious distinction. Better forecasting did not make the lakes simple. It made mariners better informed about a place that remains difficult. The surprise today is often not, no one knew a storm existed. It is, the storm evolved, focused, or expressed itself in a way that turned a known hazard into a worse one than expected. A forecast, after all, is guidance, not a force field. The NWS marine definitions show exactly how much of Great Lakes danger still lives on short clocks. Special marine warnings are issued for potentially hazardous marine weather, usually lasting up to 2 hours, including squall lines, strong cold fronts, gravity waves, or thunderstorm winds of 34 knots, or greater, that are not adequately covered by existing marine warnings. That means part of the operational reality on the lakes is that not every serious hazard is a long, leisurely event, with a full day of psychological preparation attached to it. Some of the things that surprise mariners are mesoscale and fast. the sort of developments that can make a passage much worse inside a watch-standing shift, rather than over the course of a whole afternoon. Another part of the surprise comes from the mismatch between what the lake looks like from shore and what it is doing farther out. Research on Lake Michigan wave modelling found that deep water wave conditions in the mid-lake region are often larger than in shallower or more sheltered areas, because the elongated fetch across the spacious mid-lake region can generate fully developed deep water waves, while coastal winds are impeded by the irregular coastline, and shallow water waves are strongly modified by depth-induced breaking. The same study notes that strong winds aligned along the lake's major axis can produce extreme waves in mid-lake areas more accurately than shoreline impressions might suggest. That means even a well-informed mariner can still be dealing with a basin where the dangerous part is not always the part people on land are seeing clearly. The shore can be rough, while the open lake is worse, or the near shore can be awkward, while the mid-lake has had more room to organise into something larger and more coherent. The modelling itself reflects that complexity. The same Lake Michigan study found that wave predictions in mid-lake deep water settings and in shallow and near-shore settings do not fail in the same ways, because the shallow water regions are dominated by highly dynamic interactions with bathymetry, refraction, and depth-induced breaking. In simpler terms, the deeper open lake and the shallower coastal strip are different physical problems. Modern mariners know that, but knowing it and living it are not the same thing. A captain or pilot is not moving through a single uniform sheet of forecasted water. They are moving from basin-scale wave growth into local depth effects, coastal geometry, harbour approach problems, current interactions, and whatever the atmosphere decides to add on top of that. The surprise lies partly in how quickly the governing problem changes as the vessel changes position. The lakes also keep surprising people, because not all of their most dangerous motions are the obvious ones. NOAA's operational forecast systems for coastal waters and the Great Lakes are designed to provide guidance on non-tidal sea level variations, currents, temperature, and related conditions, specifically so mariners can avoid issues such as low water and grounding risk. The NWS Marine Glossary even includes a low water advisory for Great Lakes waters when significantly below average levels create a hazard to navigation. That is a useful reminder that a modern ship can be well prepared for wind and waves and still face navigation problems caused by changing water levels, currents, or basin responses that are less visually dramatic than a gale, but still operationally serious. The Great Lakes continue to surprise because they are not just wave tanks, they are moving basins with navigation consequences. Then there is the hazard class that feels almost unfairly modern: meteor tsunamis and seiches. NOAA's 2021 National Assessment of Meteor Tsunami Risk says the Great Lakes have a dense network of coastal water level gauges, shoreline meteorological stations, offshore buoys during the ice-off season, and weather radar support. But it also notes that 6-minute water level gauges likely have limitations in capturing true peak amplitudes, and that, at that time, no systematic efforts were yet in place to address these occurrences on an operational level. That is a striking admission. Even with a fairly robust observing network, some Great Lakes water level hazards are easier to reconstruct after the fact than to fully characterise in the moment. Surprise persists because certain processes still move faster, or at scales finer than the monitoring network can perfectly resolve in real time. A very recent example makes the point better than any abstract warning could. NOAA's Great Lakes. Environmental Research Laboratory reported that the June 21, 2025 storm on Lake Superior produced a complex event involving a meteor tsunami, wind-driven surge, and strong sea activity, with a 45-inch water level rise at the Point Iroquois station in less than 2.5 hours, the largest surge in that station's 30-year record. The same event caused impacts to boating and shipping, with vessels remaining offshore to avoid groundings, dock damage, and small boats being stranded or shoved into slips. NOAA AA also noted that the fast-moving squall lines involved in such events often evolve too quickly to be fully represented in the hourly data generated by existing lake forecast models. That is modern surprise in one neat, unfriendly package. The instruments were there, the models were there, the storm still managed to produce a compound water-level event large enough to disrupt shipping and shoreline infrastructure in a very short time. It also matters that mariners are still operating in this environment at industrial scale. The Great Lakes are not a historical museum where a few nostalgic vessels keep the memory alive. The US Army Corps of Engineers said in January 2026 that more than 4,500 vessels, carrying up to 80 million tons of cargo, move through the Soo Locks annually, and that the Detroit district maintains a navigation system of 81 harbours, along with the connecting channels between the lakes. That level of traffic means professional mariners are constantly making decisions inside a living commercial system. Surprise on the Great Lakes is not an occasional recreational inconvenience. It is a standing operational problem inside one of North America's major freshwater transport networks. That commercial reality changes the meaning of modern as well. A modern mariner is not simply someone with better electronics. A modern mariner is someone moving dense cargo on a schedule through maintained channels and harbours in a system where route choices, seasonal timing, lock transits, and weather windows all matter. NOAA's wave model paper stresses that accurate forecasts of severe sea states are critical not only for public safety, but also for maritime operations with consequences for the American economy. That means the modern surprise is often not a lack of information. It is the stubborn refusal of the environment to become as orderly as commerce would prefer. The lakes still create situations where the data say one thing at broad scale, the local wave field says another, and the ship itself begins reporting a third through motion, spray, strain, and lost margin. There is also a human reason the lakes still catch people out. Forecasts arrive as numbers, zones, and text products. Reality arrives as motion. A Great Lakes Open. Lake Forecast can tell you what wind and waves are expected through day 5, and a nearshore marine forecast can be updated 4 times daily and amended when needed. But no forecast can directly transmit the bodily experience of short-period steep waves working a hull, or the way poor visibility, cold spray, darkness, and repeated impact shrink judgment. NOAA and the NWS provide increasingly sophisticated tools because the physical environment remains sophisticated in the least helpful sense. When the water is steep, the weather is changing, and the ship is already responding badly. Surprise often takes the form of escalation. Conditions do not merely worsen. They become harder to manage than they looked in the abstract. The Great Lakes also have an awkward habit of mixing old dangers with new technology, instead of replacing one with the other. The short-period waves that made the Fitzgerald storm so dangerous have not been legislated out of the basin. Michigan Sea Grant still notes that steep, short-period waves are particularly hazardous to large ships, especially above about 5 meters, and that Lake Superior can sustain waves in excess of 10 meters. Modern electronics do not lengthen those wave periods. Better communications do not make a 33-foot freshwater wave lighter. More accurate meteorology helps mariners understand the hazard earlier, but once the vessel is in it, the lake is still applying the same physics it always did. That is one of the deepest reasons the lakes still surprise people. They are modern only around the edges. At the point of contact between steel and water, they remain anciently physical. So the real answer is not that mariners keep forgetting the lessons. It is that the Great Lakes remain fully capable of creating new versions of the old lesson. They are large enough for basin-scale wave growth, complicated enough for local depth and shoreline effects, dynamic enough for non-tidal water-level hazards, and busy enough that professional crews must keep working through them, rather than admiring them from shore. Forecasts have improved, models have improved, observations have improved, but the June 2025 Lake Superior event shows that even now, a fast-moving system can combine meteor tsunami, surge and sea shea behaviour in a way that disrupts shipping and surprises communities around the lake. The lakes have not stayed dangerous because people fail to modernise. They have stayed dangerous because modernisation keeps running into a freshwater basin that still has more than one way to become unreasonable. And that is why the Great Lakes still unsettle people who know them well. Not because they are mysterious in some supernatural sense, and not because their hazards are unknowable, but because they are complicated enough to remain larger than any single forecast panel, buoy reading, or radar return. The modern mariner arrives better informed than ever, and the lake still reserves the right to answer with a faster squall line, a steeper sea, a lower water level, a sharper near-shore transformation, or a basin-wide oscillation that keeps moving after the sky has already started looking innocent again. Which is a good place to ease toward the last part of this story, because after all the steel, forecasts, wrecks and warning systems, what remains is the plainest truth of all. These waters do not need romance to command respect, only memory. And so, after all the wind and steel and hard lessons, we arrive at the quietest part of the story, which is also the most important. The Great Lakes do not need exaggeration. They do not need myth added to them. They have earned their reputation without help. They hold about 21% of the world's surface fresh water. They are routinely described by major public agencies as inland freshwater seas, and they have a long shipping history shaped by the same forces we have been following all along: fetch, steep waves, fast weather changes, cold water, hidden shoals, and the simple fact that a ship is only safe while the water stays where it belongs. That is what makes them so unsettling even now. On paper, they are lakes. In practice, they behave like a marine world with fresh water in it. The National Weather Service still maintains a full marine forecast structure for the Great Lakes, including forecast zones, open lake and near-shore products, and regularly updated marine text forecasts, because these waters continue to demand the same kind of operational respect people associate with coasts and offshore passages. That does not happen by accident. It happens because ships, crews, pilots and shoreline communities still need serious weather guidance to work around conditions that can become dangerous quickly. And that really is the plainest answer to the question we started with. Why can the Great Lakes break ships in half? Because they are large enough to build dangerous seas, restless enough to change quickly, cold enough to punish mistakes, and complicated enough to attack from more than one direction at once. The wind builds over long fetch. The waves come steep and close together. The hull is bent and worked over and over again. Water comes over the deck and lowers the ship into the next sea. Shoals and reefs begin sharpening what the storm has already made. Steel that looked permanent starts living one load at a time. None of those things sounds theatrical in isolation. Together they become catastrophic. There is something almost rude about how ordinary the beginning of danger can look on these lakes. A broad grey horizon, a little more wind than before, whitecaps that seem annoying rather than threatening, spray that looks dramatic enough for a photograph but not yet serious enough for fear. Then the fetch keeps doing its job. The waves steepen, the period shortens, the vessel starts moving in a way that is no longer comfortable. Water comes aboard more often. The deck drains less cleanly than anyone would like. A list develops. A crack matters more than it did yesterday. The ship is not destroyed in a single magical instant. It is walked toward failure by a sequence of physical events that each make the next one harder to stop. That is one reason these waters stay in people's heads. A storm on the ocean sounds expected. A storm on a lake still catches something in the mind. We think a lake should have limits. A shoreline should calm us. Land should mean refuge. But the Great Lakes do not always respect those instincts. Near shore, the bottom can make the waves steeper. Harbour approaches can become awkward. Water levels can shift. A place that looked like safety on the chart can become its own separate challenge when the basin, the weather and the bottom begin arguing with each other at the same time. It is also why the shipwrecks matter, not as decoration for local folklore, but as evidence. Thunder Bay National Marine Sanctuary protects nearly 100 historic shipwrecks, and NOAA notes that Lake Huron's cold, fresh water has preserved many of them exceptionally well. They remain below the surface not just as relics, but as repeated proof that these lakes have spent a very long time teaching the same lesson to generation after generation of mariners. The forms change. Wooden hulls become steel ones, forecasts improve, radios improve, charting improves. But the preserved wrecks keep saying the same thing in a way no lecture ever could. Fresh water can be every bit as unforgiving as salt water, and perhaps that is part of why the losses still feel close, even when they happened long before most of us were born. A shipwreck at sea can seem distant in the imagination, as though it belongs to some far place, with exotic weather and giant tides and names taken from another world. A shipwreck on a lake feels nearer. It feels domestic in the wrong way. It happened inside a body of water many people think they understand. It happened where summer cabins exist and ferries run, and families watch sunsets from public beaches. It happened in a place with picnic tables nearby. That contrast has a way of staying with people. The Great Lakes are especially good at creating that contrast because their quiet side is real. They can be calm, beautiful, and broad in a way that looks almost patient. They can lie flat under evening light and give no sign of what they are capable of later in the year or later in the same day. That is not deception. It is simply scale. A large basin does not owe us permanent roughness to count as dangerous. It only needs the right wind, enough distance, and enough time. Once those arrive together, the same calm surface people trusted in the morning can begin building itself into something that loads a hull, floods a deck, and takes away options one by one. Modern forecasting has improved the odds, and that matters. Researchers and forecasters understand far more now about storm development, wind fields, wave guidance, and lake response than they did in the eras of telegraph warnings and guesswork. But better knowledge has not turned the lakes into something tame. NOAA's Great Lakes researchers reported that a June 21, 2025 storm on Lake Superior produced a combined meteor tsunami, wind-driven surge, and Sichi event that caused a 45-inch water level rise in Whitefish Bay in less than 2.5 hours, the largest surge in that station's 30-year history. Even with modern instruments and modern models, the lake still found a way to remind everyone that it has more than one method of becoming unreasonable. That recent example matters because it clears away a comforting story people like to tell themselves. The comforting story says the old disasters belong to an older world. Weak forecasting, weak communications, weaker ship design, rougher systems, and therefore rougher outcomes. There is truth in that, of course. Modern mariners have far better tools. But the June 2025 event is a good reminder that the lakes did not surrender their physical character simply because our screens got better. Fast-moving systems, sudden water level changes, steep waves, and local effects still exist. The surprise has not disappeared. It has only changed shape. And maybe that is the fairest way to put it. The Great Lakes still surprise modern mariners not because mariners have learned nothing, but because the lakes remain larger than any one person's confidence. They are still wide enough for fetch to matter. They are still cold enough for immersion to matter. They are still shallow in the wrong places and deep in others. They are still able to turn a weather problem into a deck problem into a flooding problem, and a flooding problem into a structural problem. The exact sequence varies. The physics does not. It is worth remembering too that ships do not go onto the lakes to pose heroically against storms. They go there to work. Ore has to move. Grain has to move. Stone, coal, steel, fuel, and all the rest of it have to move through a system that remains commercially important and heavily used. That working quality changes the emotional tone of the whole story. These are not fantasy voyages into danger for the sake of drama. They are practical trips through a practical system where practical people do serious jobs in a place that can become very impractical very quickly. The danger is not theatrical to them. It is part of the day's calculations, and that, strangely enough, is what makes the subject feel calmer once you understand it. The lakes are not malicious. They are not mysterious in some supernatural way. They are simply physical and very large and very capable of punishing poor timing, reduced margin, and wishful thinking. Once you see that clearly, the fear becomes more precise. It becomes respect. Respect is easier to carry than vague dread because respect has rules attached to it. Watch the weather, respect the fetch, respect cold water, respect the chart, respect the wave period, not only the wave height. Respect the fact that water on deck is no longer just weather. Respect the fact that a long steel hull is strong, but not infinitely strong. There is a kind of honesty in that. A place this large does not ask for admiration. It asks for correct judgment. That may be the most useful conclusion of all. We do not have to speak of the Great Lakes as if they are monsters. We only have to stop speaking of them as if they are small. The danger begins there, in the word small, or even in the word lake when it is used carelessly. A smaller word invites smaller habits of mind. It invites people to compare Superior or Huron to waters that have none of their scale, none of their fetch, none of their freight traffic, none of their preserved wrecks, and none of their history of turning bad weather into remembered names. So perhaps the real power beneath the surface is not only in the water itself, but in the way the lakes refuse simplification. They will not stay in one category for us. They are scenic and industrial, familiar and dangerous, freshwater and still fully maritime in consequence. They are places where a beach day and a shipping casualty can belong to the same basin, separated only by distance, season, and a change in wind direction. That refusal to become simple is what keeps them important. It is also what keeps them humbling. And now, after all of this, I find myself returning to the image we began with. Not the most dramatic one, not a ship already foundering, not a wall of water crashing over a bow in darkness. Just a broad stretch of lake under a heavy sky, where the surface still looks almost manageable if you do not know what comes next. That is where the whole story lives, in the gap between appearance and force, in the distance between calm-looking water and the wave field it is becoming, in the quiet confidence of steel before the sea begins testing every joint, every cover, every frame, and every assumption. If you're listening tonight from somewhere near one of the Great Lakes, you may know this feeling already. The weather report shifts a little. The wind rises. The colour of the water changes. The shoreline looks the same, but not quite. You do not need to be a mariner to sense that the lake is in a different mood. And if you are listening from far away, perhaps that is the thing most worth taking with you. Not that the lakes are legendary, though they are. Not that they are dangerous, though they certainly are. But that size and danger do not always announce themselves with exotic names. Sometimes they sit in the middle of a familiar map and wait patiently for us to underestimate them, which, in its own way, is why this subject suits a quiet ending. The loud part of the story is easy. The storm, the wave, the wreck, the split hull, the last transmission, the list of the lost. Those are the parts people remember first. The quieter part is what stays after. The accumulated respect. The realization that nearly every disaster we have talked through tonight came from understandable forces acting in understandable ways. The wind was not magical. The steel was not cursed. The water was not angry in any human sense. It was only heavy, cold, moving, and given enough room to do what physics allows. And maybe that is exactly why the Great Lakes deserve so much respect. They do not frighten us with fantasy. They frighten us with reality, with the plain weight of water, with the hard limit of steel, with the steady truth that a ship is safest while its margin is still intact, and that margin can disappear faster than pride would ever like to admit. There is something sobering in that, but there is also something clean about it. The lesson is hard, but it is clear. So wherever you are tonight, and whatever the water near you happens to be doing, I hope this little journey has left you with the right kind of caution. Not nervousness, not melodrama, just the steady understanding that some landscapes are more powerful than their names suggest, and that the Great Lakes are among them. Inland, yes. Freshwater, yes. But never small in the ways that matter. And if you found this strangely calming, or useful, or just the right sort of serious to end the day with, then I'd be glad to have you here again. You can leave a like, subscribe, and share this quiet corner with someone who enjoys the slower kind of storytelling, the kind that takes a simple question and follows it all the way down until the answer begins to sound less like a fact and more like a habit of mind. For now, though, let the ships rest where they are, let the forecasts keep watch, and let the lakes remain what they have always been: broad, cold, busy, and capable of far more force than a casual glance would ever suggest. Sleep well, and wherever you are listening from tonight, may the water nearest you stay on the peaceful side of its nature.